When most of us think about the world around us, we picture things existing in a definite state and moving in a predictable way according to classical rules like Newton's laws of motion. But over a century ago, scientists began to realize that on extremely small scales, matter and energy don't always behave so definitively or neatly. A brand new theory called quantum mechanics was needed to describe what was happening at the molecular, atomic, and even tinier levels. Quantum physics introduced an entirely new way of looking at reality. Its central implication is that nature works according to probabilistic laws rather than definite ones. Things aren't always precisely where we expect, doing exactly what we predict. Quantum physics also proposes that particles can take on attributes of both particles and waves, a confusing possibility not envisioned by classical theories. It suggests that particles can influence each other instantaneously even across vast distances, and it raises deep questions about the nature of existence itself. So in essence, quantum mechanics is the physics that describes the universe on subatomic scales, the behavior of matter and energy at the level of atoms, electrons, and smaller constituents like photons, quarks, and more. It explains how these tiny particles can exhibit properties corresponding to both particles and waves, and how they can become non-local or entangled with each other. There is no universally agreed upon cutoff point where the quantum laws cease to apply and classical laws begin. But in general, quantum mechanics deals with the very small, while classical physics handles interactions visible to our everyday senses. Some key areas where quantum physics departs radically from classical expectations are: particles often exhibit wave-like properties such as diffraction and interference. According to classical physics, particles should always behave just like particles, not waves. But experiments show electrons, photons, and other particles can display behaviors only waves could produce. This suggests a particle is somehow a quantum bundle containing both particle and wave attributes. There is a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time, due to Heisenberg's uncertainty principle. In the quantum realm, we cannot predict all dynamic properties of a system simultaneously, as classical theories assumed. Some quantities are essentially unpredictable even in theory. Particles can dynamically switch between different quantum states in apparently random ways. Quantum theory sees particles not as hard little balls, but as quantum fuzz described by wave functions that evolve in time. These wave functions encode probabilities for the possible states a particle might adopt upon measurement. Particles are able to tunnel through barriers they could never surmount classically. Electrons, for example, routinely squeeze through potential energy barriers that classical dynamics would deem impossible to penetrate. Quantum tunneling allows radioisotope decay and is important for devices like flash memory. Systems can become non-locally entangled in ways that relate particles over arbitrarily large separations instantaneously. If you measure one particle of an entangled pair, the state of its distant twin partner will be determined instantly however far apart they are, faster than signals could propagate classically. Individual quantum events, like photons striking eyes or Geiger counters clicking, arise through purely probabilistic quantum jumps rather than any continuous or predictable mechanics. Quantum processes are non-deterministic, evolving based on probabilities rather than definite laws. So in summary, the core departure of the quantum realm is its acceptance of what we might call ghostliness, the ability of entities to exhibit wave-like properties as well as particle properties, to blend both definiteness and uncertainty, and to potentially act non-locally across space itself. All of this was deeply strange and metaphysically troubling to the founding scientists of quantum mechanics in the early 1900s. But there was also clear evidence something beyond classical physics was going on. For starters, experiments showed that shining light or electron beams at tiny slits produced interference patterns, stripes of stronger and weaker intensities on a detection screen, as would be expected if the beams were waves. How could point-like particles somehow interfere with each other like waves? Similarly, precise measurements of the light emitted and absorbed by heated objects showed it came and went in precise discrete quanta, challenging our notions of energy as a continuous fluid. Black body radiation experiments conducted by Max Planck in 1900 showed that the energy of electromagnetic waves emitted by hot objects could only change in integer multiples of a specific minimum quantum. This led Planck to propose the first quantum hypothesis and helped establish the field. Einstein later explained the photoelectric effect in 1905 by suggesting light itself comes in localized packets of energy, later dubbed photons. Around the same time, Niels Bohr put forth his quantum model of the atom, where electrons can only inhabit certain permitted stable orbits and jump between them by absorbing or emitting photons of precise frequencies. Louis de Broglie then theorized in 1924 that not only does light act as a particle as photons, but conversely all matter could also exhibit wavelength properties, as was later verified experimentally for electrons. This helped cement the idea that quantum entities have a dual wave-particle nature. Then, in 1925, Werner Heisenberg and Erwin Schrödinger independently formulated the key mathematical frameworks of matrix mechanics and wave mechanics respectively, building on de Broglie's duality principle. When combined, these early theories formed the core conceptual architecture of what we now call quantum mechanics. Subsequent experiments confirmed many predicted quantum phenomena were real. For example, electron diffraction experiments performed by Davison and Germer in 1927 showed electrons impacting the crystal-produced interference patterns, proving they demonstrate wave-like behaviors. Other discoveries cemented new quantum principles, like the Pauli exclusion principle showing electrons within atoms cannot all occupy the same quantum state, or cloud chamber pictures revealing the discontinuous particle-like jumps of radioactivity. Modern particle accelerators and other precision instruments have revealed many more quantum subtleties hidden in our everyday matter. So while seeming bizarre and logically contradictory, the predictions of quantum physics have held up again and again through over a century of experimental testing. Many technologies utilizing quantum effects have become integral to society, from the solid-state electronics powering computers and smartphones to medical imaging with technologies like MRI. Even greater applicability may emerge as quantum computing, cryptology, and other fields mature. Despite its strangeness, quantum mechanics has proven remarkably accurate at forecasting behaviors in experiments involving electrons, photons, atoms, and more. It revolutionized how we understand the tiniest realms of the natural world. So in summary, the revolution brought on by quantum physics was recognizing that at submicroscopic scales, nature works according to an entirely different set of principles than we experience at human scales governed by classical laws. Properties like position and momentum become fundamentally probabilistic. Waves and particles merge into an ambiguous duality. Cause and effect give way to uncertainty. Non-local influences appear to arise, and discrete quantization governs exchanges of energy and other dynamics. This introduced a radical new worldview, as strange as any metaphysics, yet one that has repeatedly proven itself through experimental verification. Quantum theory opened a strange new territory for science to explore piece by piece over subsequent decades, revealing ever deeper mysteries underlying our everyday reality. One of the most directly perceptible manifestations of the quantum mechanical nature of our world is the dual wave-particle behavior exhibited by both light and microscopic particles of matter like electrons. According to the foundations of quantum physics, elementary entities partake of properties associated with both waves and particles, a blend that confounds our classical intuitions but has been clearly demonstrated through experimentation. Light behaves not merely as streams of photon particles, but also as an electromagnetic wave. while electrons and other minuscule ingredients of atoms manifest signatures of quantum waves in addition to their particle attributes. Understanding this bimodal essence of quantum objects has been pivotal to advancing modern physics. To set the stage, we must go back to what was known before quantum theory emerged. Classically, waves were understood as disturbances that transport energy by virtue of periodic oscillatory motion, transmitting this energy from one location to another without requiring a material medium, like ripples propagating across water. While waves could interact, interfere, refract, and diffract, they were seen as fundamentally different from particles, conceived of as localized granular blobs of matter. Light, too, had traditionally been depicted as a wave, first hypothesized as undulations in an invisible ether permeating all space. Particles, by contrast, were envisioned as discretized clumps of stuff following definite trajectories under forces. According to classical mechanics, particles like bullets and balls should always act as straightforward moving bits devoid of wave-like properties like diffractive interference. Conversely, waves like water ripples or sound were supposed to lack qualities reserved for particulate objects. They couldn't be confined to specific points nor possess momentum and kinetic energy. In the late 19th century, evidence accumulated that this classical dichotomy failed to explain nature at the atomic scale. Maxwell's unification of electricity, magnetism, and light predicted that electromagnetic waves included a spectrum spanning from radio to visible light to X-rays. But how could a unified theory of light as waves still account for observations like the discrete quantization seen in black-body radiation spectra? Then in 1905, Einstein proposed his photoelectric effect theory, attributing the ejection of electrons from metals struck by light to discrete quanta of the light's energy, later termed photons. This particle-like behavior conflicted with the wave depiction of light. Around the same time, Rutherford was bombarding thin gold foils with alpha particles and unraveling the nuclear structure of atoms, showing matter itself was concentrated in a minuscule volume at the core despite its low density, much like a planetic system. It became evident the classical conception was breaking down. Matter and light both exhibited puzzling signatures not predicted by standard theories of particles or waves alone. A new paradigm was clearly required. In 1924, Louis de Broglie boldly theorized that not only should light quanta act as particles sometimes, but conversely all matter, including electrons, must also manifest wave-like properties, opening a path to reconcile these anomalies. Within a year, this idea was confirmed experimentally. Davison and Germer at Bell Labs fired a beam of electrons at a nickel target and observed an interference pattern, the signature stripes and valleys indicative of waves, on a phosphorescent screen behind it. The electrons were interacting not individually but collectively as a quantum wave, since a wave description predicted the observed interference and a particle picture did not. This landmark double-slit experiment with matter entities proved to be broadly correct and established that all quantum objects partake of dual properties. Let us now examine in more depth precisely how this particle-wave duality manifests itself for both light and minute entities like electrons. We will start with visible light, since its wave nature has long been evident from phenomena like thin film interference and single-slit diffraction patterns. When a beam of light encounters an obstruction in its path, say two narrow slits side by side, it does not interact with the slits as just individual photons. Rather, the light propagates from the slits as concentric spherical waves that then overlap and interfere with each other, forming characteristic interference fringes on a screen, the signature of a wave. The brighter and darker bands show how at some points the peaks of one wave crest aligned constructively with another to enhance intensity, while elsewhere troughs cancelled peaks out in destructive fashion. This undeniably wave-like behavior is starkly at odds with envisioning light as a stream of discrete particles. Yet we also know light definitely exhibits particle-like attributes. individual photons, measured precisely one by one, retain their individual quantized energies corresponding to their frequencies. They activate single detectors without spreading out, hit with local impact. The photoelectric and Compton effects prove light interacts in localized discrete quanta. So visible light is both wave and particle simultaneously. Its energy comes in grainy units of n photons, but it propagates interferingly as a continuous electromagnetic wave. The same dual nature applies to electrons and other microscopic atomic constituents. Electron microscopes use electrons as probing bullets, whereas low-energy electron diffraction reveals their wave-like interference patterns impacting crystal lattices. Electrons also tunnel quantum mechanically, a phenomenon only a wave could achieve. At a deeper level, quantum mechanics depicts all fundamental particles not as hard little spheres, but as infinitely spread wave functions defined throughout space that evolve dynamically according to Schrödinger's equation. These probabilistic wave functions encode where particles might be located upon measurement and interfere just as classical waves do. So, at their essence, particles are spread quantum ripples rather than localized billiard balls, even as experiments pin them down to points. The wave function collapses from spread quantum state to definite particle position upon observation. Likewise, microscopic entities also scatter and diffract, leaving interference patterns to betray their underlying quantum wave nature. These include not just electrons, but massive particles like neutrons, atoms, and even whole molecules. Experiments have demonstrated diffraction of C60 buckeball molecules, for instance. The fuzzier the quantum state, the more washed out the interference fringes. But all fundamentally quantify matter in a manner betraying its intermediary particle wave character. So in summary, both light and microscopic matter exhibit a melange of attributes associated with both particles and waves, according to quantum theory. Photons and electrons do not fully conform to classical definitions of either concept, partaking instead of a murky dualism. Their energies quantize, yet they diffract interferingly as spread wavelengths. They localize yet tunnel fluidly like quantum ripples. At their essence, all quantum objects retain a ghostly haziness transcending classical delineations, interacting dually now as particle now as wave, depending on observation. Reconciling nature's quantized discreteness with its continuous fluidity required a paradigm shift to the field of quantum physics. The breakthrough discoveries that precipitated quantum mechanics fundamentally transformed our conception of matter itself, and especially how electrons interact with atoms on the tiniest scales. Prior to the early 1900s, the notion of the atom as the basic building block of all substances was well established thanks to scientists like John Dalton. But what atoms actually were in their innermost essence remained mysterious. It was only through applying quantum theoretical principles that we began to fathom the strange quantized motions and structures within atoms that make chemical reactivity and our observable world possible. At the atomic scale, classical mechanics simply could not reconcile what was being observed. James Clerk Maxwell's work on electromagnetism in the 1860s had greatly advanced knowledge of light, fields, electricity, and heat. But one perplexing contradiction remained. How could a heated object concentrate its radiation into specific bright emission spectro-reflecting temperature, as seen through prism spectrometers? According to classical electromagnetism, radiation from any excited body should be emitted uniformly at all wavelengths in a continuous smear. The breakthrough came from Max Planck in 1900. By proposing that electromagnetic radiation could only be emitted and absorbed in discrete quantized packets of energy, each proportional to its frequency, by a new universal constant and now called Planck's constant, Planck was able to perfectly explain the signatures of black body curves. Light and other EM waves thus came in photon bites, proportional to frequency, resolving the dilemma. It was the origin of the quantum hypothesis. Around 1905, Albert Einstein took the next bold step by theorizing that not only is light emission quantized, but light itself consists of localized discrete quanta we now term photons. Using this concept, he was able to elegantly explain experimental mysteries like the photoelectric effect, where shining light on certain materials could eject loosely bound electrons. The ejected electrons retained specific kinetic energies directly proportional to photon frequency above a threshold, not the amount of light falling on them as classical theory predicted. Photons convincingly behaved like particles. Meanwhile, experiments on cathode ray tubes were probing the internal structures of atoms. In 1897, Thomson discovered that beams of cathode rays were deflected by electric and magnetic fields in regular ways, exhibiting a common mass-to-charge ratio. Thomson rightly deduced these particles, which he called corpuscles, must be subatomic constituents of atoms over 1800 times lighter than hydrogen, what we now call electrons. Soon after, various scientists, including Ernest Rutherford and Hans Geiger, began systematically bombarding very light atoms with alpha particles, providing deeper atomic scale insights. Rutherford noticed that rather than passing straight through as classical mechanics would expect, some alpha particles would bounce backward off gold foil at wide angles. This could only be explained if the mass of entire gold atoms was concentrated to a tiny dense nucleus at the center. Rutherford thus established the planetary model of the atom in 1911, where electrons in circular orbits surrounded a tiny but massive positively charged atomic nucleus containing elemental protons and neutrons. It explained so many previous experiments, but deep inconsistencies with quantum theory soon became apparent even in this improved model. Chief among them was how electrons orbiting a nucleus should continuously emit energy through electromagnetic radiation according to Maxwell's equations as accelerated charges spiraling into the center on microscopic timescales. This dilemma ushered in the first quantum solution proposed by Niels Bohr in 1913. Bohr postulated that within atoms, electrons instead occupy only certain discrete, stationary states, fixed at specific energy levels, instead of freely radiating away energy. Transitions between these atomic shells could explain spectral lines seen in atomic emission and absorption. Bohr also theorized such jumps necessitated emission or absorption of precise photon packets matching the energy gaps between levels as per Planck-Einstein's light quantum hypothesis. Bohr's model provided answers matching experimental spectra beautifully and explained stability within atoms. But its rules were introduced only as empirical correlations, leaving their deeper justification mysterious. The true foundations emerged with developments by Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others applying matrix mechanics and wave equations to electrons fully quantum mechanically, not as classical particles. Their work showed the electron cannot be precisely localized, but is rather described by a wave function spread throughout the atom. This wave function encodes the likelihood of finding the electron somewhere via its quantum probability amplitude. Importantly, only certain standing wave patterns with nodes and antinodes matching the atom's size are allowed by the quantum mechanical boundary conditions, forming the orbitals we now know. The electron's position and momentum become inextricably uncertain, according to Heisenberg, an attribute of its underlying quantum mechanical nature rather than any observational limitation. Detection collapses its probabilistic waveform into a point. More fundamentally, the electron is not a localized billiard ball, but an infinitely spread non-particle described mathematically. Its behavior is utterly strange from our classical Newtonian intuitions. For example, due to its quantum mechanical spread, the electron maintains no well-defined trajectory, but tunnels right through potential energy barriers it seemingly shouldn't be able to classically. We can consider it neither wave nor particle alone, but something new, a probability wave shape behaving according to the laws of quantum superpositions. With this theoretical framework, experiments could be explained far more profoundly than the crude early atomic models. Phenomena like the discrete lines of atomic emission spectra arise because electrons can only stably exist quantum mechanically within the permitted quantized orbits corresponding to permissible wave functions matching the atom's size and potential well. Transitions necessitate absorption or emission of photons with energies matching the gaps, populating higher or lower orbits. On smaller scales within atoms, even protons and neutrons in the dense nucleus display quantum behavior described by quantum chromodynamics. Their interactions are shaped by phenomena like spin, cover charge, and mediated by force carrier particles like gluons. All the way down, even quarks as fundamental constituents of protons and neutrons exhibit bizarre quantum properties and relativistic strangeness utterly unlike anything known to classical physics. At its root, matter is governed by principles both alien yet profoundly precise. In summary, applying quantum mechanics to understand atoms revealed that electrons whirring within are not hard particles following classical trajectories. Their behavior is governed by the bizarre quantum probabilistic wave mechanics of delocalized wave functions and constrained quantum states. Only certain standing wave patterns consistent with atoms' boundaries are allowed stable orbits within which electrons probabilistically exist. This understanding of the quantized quantum nature of atoms forms the basis of all modern physics, chemistry, and material science governing our world. One of the most iconic and counterintuitive revelations of quantum theory is Werner Heisenberg's uncertainty principle, which places fundamental probabilistic limits on how precisely certain pairs of physical properties of quantum systems can be known simultaneously. According to this foundational principle of quantum mechanics, there exists an intrinsic fuzziness and lack of definite answers at the quantum realm due to an inextricable correlation between measurements made and random fluctuations triggered within a system. It demonstrates nature possesses an intrinsic indeterminism even in theory, and shook physicists' faith in a precisely knowable universe. To motivate this strange principle, let us first recall what the classical worldview assumed. In classical mechanics, objects have definitively demarcated positions and momenta at any instant, which can be measured precisely and independently of one another according to Newton's laws. An object's trajectory through space and time was envisioned as a clearly delineated path governed by deterministic formulas. While experimental uncertainty arising from imperfect instruments placed practical limits on accuracy, in theory the future of any system could be predicted perfectly from initial parameters. However, the emerging field of quantum mechanics based on Planck's energy quantization and Einstein's light quanta was challenging this paradigm on observable fronts. Black body radiation and the photoelectric effect could not be explained classically. Atoms gave off and absorbed energy in precise multiples of Planck's constant depending on quantum jumps. Electrons behaved dually as waves interfering and particles localizing. De Broglie discovered matter too demonstrated wavelength properties, with electrons diffracting like waves. A new probabilistic conceptual framework was clearly required. Heisenberg's breakthrough came as he pondered analogous behavior in the light microscope, how resolving finer spatial details necessarily blurs details of a particle's momentum due to scattering photons. This pointed to a deeper correlation constraining what could be simultaneously known about conjugate variables like position and momentum. In 1925, Heisenberg mathematically derived his uncertainty principle by analyzing quantum commutation relationships between non-commuting observables using the newly minted quantum formalism known as matrix mechanics. In its most well-known form, the uncertainty principle places a lower bound on the precision with which certain observable quantities, like a particle's position and momentum, can be estimated at the same time. It states that the more precisely one property is measured, the less precisely the other becomes known. Specifically, the uncertainties in position x and momentum of a particle must satisfy. This means for all quantum systems, no measurement can ever simultaneously determine both the particle's location and momentum and velocity with arbitrarily high accuracy. The product of their uncertainties must always exceed a minimum value set by. The deeper implication is nature itself appears to contain an intrinsic randomness governed by probability distributions rather than certainty, an outcome of linking observation to the system through quantized exchanges of energy and information. To appreciate the radical departure from classical determinism, consider an experiment where a beam of electrons is aimed at a detecting screen. Using a microscope, one might try to image an electron's precise point of impact, but the photon used to detect its position will disturb its momentum by an uncertain amount due to transfer of momentum. Conversely, attempting to precisely measure momentum via many repeated collisions will diffuse and blur the position. There exists an inescapable trade-off between resolving conjugate variables according to nature's laws. One way to intuitively grasp this is imagining zooming in microscopically to observe a quantum event. Our probe inevitably jostles the system due to its own quantum properties. This embeds a fuzziness preventing simultaneous sharp definition of canonically conjugate observables like x and p. More fundamentally, in matrix mechanics, non-commutativity of complementary variables arises from the underlying quantum state space mathematics, forcing the correlation between intrinsic randomness and precision of knowledge. It's important to emphasize some key points about this principle. Firstly, Heisenberg's relationship demarcates fundamental limits in nature itself due to the quantum nature of measurements, not just practical observational limits. It holds even with perfect instruments. Also, it applies universally to all quantum systems from electrons to entire buildings, though uncertainties may be minuscule at large scales. And it governs any observables linked by canonical commutation relations, like angular position/momentum. Some profound implications emerged. If properties like location cannot be demarcated precisely in a single quantum entity, then perhaps our notions of objectively existent trajectories break down. Quantum jumps suggested an intrinsic stochasticism to dynamical processes. Additionally, Heisenberg's work highlighted the observer cannot be divorced from what is observed. Measurement disturbs the measured. This challenged hopes of objectively describing a pre-existing reality independently of observation. Heisenberg himself took these insights as signaling reality exists in a statistical view rather than definite states. Many prominent physicists, like Einstein, remained deeply troubled by what they saw as an unacceptable injection of human uncertainty into the natural world. Yet the explanatory and predictive power of quantum theory could not be denied, and Heisenberg's principle was quickly proven through experiments. For example, gamma-ray microscopes revealed complementary uncertainty trade-offs between position and wavelength resolutions. Since Heisenberg, the uncertainty principle has been extended and applied in diverse quantum realms, from atoms to photons to larger objects. It is perhaps the most viscerally realized proof that at microscopic and smaller scales, nature simply does not conform to classical determinism and requires inherently probabilistic quantum logic to describe it. Even today, experiments continue pushing uncertainty bounds and applications in nanotechnology probe quantum limits on measurements. Ultimately, Heisenberg uncertainty signifies reality possesses intrinsic randomness and ambiguity that may result from a deeper linking between observer and observed at a fundamental level. It reveals nature as probabilistic rather than precisely predictable in a way deeply confounding to common sense, yet crucially empowering quantum theory to model the microscopic world with unprecedented accuracy denied to classical depictions. One of the most counterintuitive predictions of quantum theory is the strange phenomenon of quantum tunneling, which allows particles to traverse energy barriers they seemingly could never surmount according to classical physics. At the quantum scale, entities can behave in a manner defying our expectations based on everyday experience, penetrating barriers that would appear impossible. This mysterious effect underlies crucial processes throughout nature yet confounds our instincts. It strikingly exemplifies how quantum reality diverges from classical reality and shows the powerful yet bizarre ways quantum probability distributions can supplant definite trajectories. To set the stage, recall that in classical mechanics, an object can only cross an energy barrier if its total kinetic plus potential energy is greater than the barrier height. Anything with insufficient energy should be unable to penetrate the obstruction and rebound from its boundary. Conversely, quantum theory prescribes entities as spread probabilistic wave functions. These can extend into formerly forbidden regions with non-zero probability amplitudes, allowing occasional penetration. For example, radioactive alpha particles tunneling clean out of atomic nuclei, despite being energetically trapped within. Tunneling arises due to the intrinsic waviness of quantum objects, their wavelengths extending beyond classically circumscribed regions. To simplify, envision an electron approaching a barrier like a sheet of insulating material or potential energy high as per Schrödinger's equation. Classically, it would need surplus energy to leap over this obstruction. But its quantum wave function penetrates with diminishing yet non-zero amplitude inside the barrier itself, reflecting and transmitting constructively or destructively. By probability conservation, a small portion transmitting completely on the other side constitutes tunneling. Higher energy electrons tunnel more readily, with longer wavelengths penetrating further inside barriers before reflecting, explaining energy dependence. Importantly though, no single electron trajectory transits the obstruction. Only the collective quantum wavedom describes an ensemble tunneling probabilistically. This baffling effect enables phenomena denied to classical physics. Quantum tunneling underlies radioactivity, allowing alpha, beta, and gamma rays to escape atomic nuclei, which classically could not. It helps explain cold electricity emission enabling field electron and ion microscopes. It allows scanning tunneling microscopy's atoms' deep resolution by sensing tunnel current between probe tip and sample. Tunnel diodes exploit a negative resistance region where tunneling dramatically increases current. Esaki and Kazuo helped uncover this in the first quantum effect transistors. In essence, all subatomic and atomic scale phenomena involve tunneling since particles significantly interact through barriers like potential energy wells and nuclear surfaces. Even macroscopic classical processes engage quantum tunneling on small scales when thermal or electrical excitation permits occasional penetration. For instance, some chemical reactions proceed via tunneling, transferring hydrogen atoms or breaking bonds quantum mechanically. One macroscopic example is field electron emission from sharp metallic tips, used industrially in flat panel displays and vacuum tubes since the 1920s. An intense electrostatic field near a nanoscale pointed protrusion lowers the vacuum potential barrier enough for electron wave functions to penetrate by tunneling, ejecting currents detectable in vacuum. Similarly, scanning tunneling microscopes utilize tip sample electric fields inducing tunneling currents, sensed as atomic scale resolution topographies. At larger scales, quantum tunnel ionization has been observed in methane gas when bombarded with intense laser pulses, ionizing the molecule by allowing its electron cloud to quantum mechanically extend beyond the nucleus enough for ejection. Some exotic tunneling-based proposals even posit ways quantum-driven artificial cold fusion or new propulsion could theoretically operate via enhanced penetrations between reactant nuclei. In more mundane contexts, quantum tunneling proves crucial for modern device nanofabrication. Scanning probe lithography utilizes tunneling tips to locally oxidize or etch surfaces atom by atom, enabling nanoscale electron circuit printing. Flash memory chips erase stored data via Fowler-Nordheim tunneling, where electrons tunnel through thin oxides to erase floating gates on demand. And tunnel junctions form the basic units within quantum computing technologies seeking to capitalize on quantum parallelism. So in summary, quantum tunneling denotes the peculiarly quantum mechanical phenomenon where entities can traverse spatially restricted regions denied to them classically via non-zero probability wave function amplitudes penetrating energy barriers. This allows corpuscles to sometimes circumvent obstructions in abnormally high energy states, essentially unattainable through classical mechanics alone. Though strange, tunneling proves all-pervasive on small scales, underpinning phenomena from radioactivity to microscopy to transistors to even potential future quantum technologies. It dramatically exemplifies the bizarre yet practically potent shortcomings of classical logic in the nanoworld. One of the most fanciful notions emerging from the strange framework of quantum mechanics is the concept of quantum entanglement, a linkage correlating properties of quantum particles even when separated by vast distances, defying our classical intuitions. Entangled systems retain non-local connections, seemingly allowing instantaneous influence between distant parts, despite locality being a core tenet of relativity. Though still not fully understood century after its prediction, entanglement is being harnessed in developing quantum technologies from cryptography to computing, and may help unravel mysteries of space-time itself. The inseparable interconnectivity of entangled particles was first noted theoretically in the 1930s by Albert Einstein, Boris Podolsky, and Nathan Rosen in what's known as the EPR paradox paper. To Einstein and his collaborators, the holistic correlations predicted by entanglement were deeply unsettling, suggesting physics was incomplete if it didn't factor in underlying elements of reality. But in 1964, Irish physicist John Bell derived an inequality showing how entanglement should statistically violate local hidden variable theories attempting to preserve causality. In 1982, French scientists Alain Aspect and his collaborators performed the first conclusive experiment verifying such non-local connections using entangled photon polarizations. Since then, countless tests have upheld Bell's theorem proving nature does exhibit the strange non-locality of entanglement. Two entangled particles essentially share a single quantum state described by an entangled wave function, such that measuring one instantly projects the outcome of its entangled twin regardless of separation per the Copenhagen interpretation. Entanglement furnishes non-classical correlations that cannot be simulated with local hidden variables. For example, entangling photons' polarizations results in perfectly anti-correlated measurement outcomes no matter the polarity detector settings, a phenomenon immortalized as quantum weirdness. This remains true even if measurements are performed faster than signals could travel between separated entangled photons, which seem to coordinate instantly across space in defiance of relativity. Mathematically, entanglement arises from superposing quantum states. Entangling two photons places them in a superposition spanning multiple possibilities simultaneously, like both vertically polarized and both horizontally polarized at once. Collapse upon measurement randomly determines a single outcome for each photon, respecting quantum probability amplitudes encoding their inextricable link. This holistic bond between entangled twins persists until decoherence disentangles them via environment interaction. Any interaction capable of uniting distinct quantum systems into a single entangled whole produces correlations able to be exploited. For example, during some types of particle collisions producing pairs of bosons like pions or photons, momentum is conserved within quantum uncertainties. This sows the seeds of momentum position entanglement between collision products speeding off together before separating. Similarly, collisions within Bose-Einstein condensates, atom lasers, and other quantum systems can entangle properties like spin, energy, or position within the shared quantum state of participating entities. Perhaps entanglement's most tangible application so far is in developing quantum cryptography. theoretically unbreakable protocols whose security hinges on ability to detect eavesdropping via entanglement disturbance. By transmitting one photon from an entangled pair over each line, any measurement or interception becomes detectable through violation of Bell's inequality certified by measurements on the other retained photon. Commercial quantum cryptography systems use polarization or phase-entangled photons to bake internet-scale amounts of certified random numbers for one-time paths or key distribution. Entanglement also forms the basis for envisioned quantum computers, which could solve certain problems millions of times faster than classical computers using massive qubit networks in entangled superpositions spanning quantum parallel universes of computation. Though challenging, steady experimental progress, integrating and manipulating ever larger arrays of coherently entangled elements like photons, ions, and superconductors aims to realize the full potential of general quantum information processing some decades hence. On a foundational level, entanglement poses deep questions about spacetime and quantum cosmology. Could the observed connections between vastly separated particles suggest a more profound substratum underlying spacetime geometry itself, as posited in emerging quantum gravity theories like holographic models see universe borders as projection screens encoding quantum information? Deciphering the ultimate meaning of entanglement and whether or how information locality might emerge from quantum entanglement at grander scales remains an open problem unifying gravitation and quantum mechanics. But for now, entanglement has proven a remarkably robust resource for quantum protocols, even if its stranger implications leave our classical intuitions fundamentally rattled. As the bizarre principles of quantum mechanics are applied to information processing, they promise revolutionary abilities beyond the scope of digital computers by harnessing nature's inherent parallelism and ambiguity. Still in its early stages, the nascent field of quantum computing capitalizes on phenomena like superposition, entanglement, and tunneling to exponentially speed up solving certain complex problems, with applications envisioned across sciences, engineering, and even mathematics. If quantum processors can be adequately scaled, they may transform industries from drug design to finance to material science, too challenging for today's classical algorithms. At the heart of quantum computing's prowess is representing information using quantum bits or qubits, quantum systems like electrons, photons, or atoms with two observable states analogous to zeros and ones in a classical bit. But unlike everyday bits confined to one state or the other, a qubit can exist in a superposition of both 0 and 1 concurrently due to its quantum nature. Multiple interconnected qubits can together inhabit an entangled state spanning all possible combinations simultaneously, an exponentially vast parallelized space of potential solutions. Quantum algorithms strategically construct and manipulate such quantum superpositions to efficiently solve problems intractable on classical machines. For instance, using quantum phase estimation to enact a Fourier transform in place, allowing problems like integer factorization or simulations of quantum systems many times faster. Other algorithms like Grover's search or HHL lever quantum tunneling, superdense coding or measurement to provide quadratic or even exponential advantages over classical approaches for pattern matching, data sampling, or linear algebra problems. At a basic level, quantum circuits work analogously to classical circuits with qubits replacing bits and reversible unitary quantum logic gates replacing irreversible logic gates. Gates induce conditional phase shifts within qubit superposition states through tools like quantum tunneling, entanglement, or controlled interactions. By strategically facing interference between computational basis states, algorithms sculpt entangled wave functions representing solutions until readout collapses distinct possibilities. while fragile, carefully crafted quantum gate sequences coherently solve problems riding quantum parallelism's razor's edge. In essence, quantum computers temporarily harness the dizzying parallelism of quantum superpositions to speed calculations beyond classical capacities, but only if measurement can intelligently extract useful data without irreversibly destroying those superpositions, which encode exponentially many potential solutions simultaneously. Quantum error correction aims to surmount fragility using redundant encoding and syndrome extraction, though scaling this seamlessly remains experimentalists' foremost challenge. Early proof-of-principle quantum processors exist using technologies like ion traps, superconducting circuits, and integrated photonics. In 1998, IBM Quantum Experience platform demonstrated a 3-qubit chip, whereas 2008 to 2013 marked scaling successes for Wave's quantum annealing approach targeting optimization problems. Google's 72-qubit Bristlecone chip in 2018 marked a major milestone, though its qubits were still error-prone and limited to specific tasks. Topological quantum computing also rose as a viable approach using inherently fault-tolerant anyons. Scaling to the multi-thousand qubit level with high coherence and connectivity needed for quantum supremacy is an immense engineering challenge, requiring unprecedented levels of isolation, control, and integration. Even fault-tolerant surface code quantum error correcting approaches using millions of physical qubits may be required to actually run practical error-corrected algorithms. But immense recent progress in coherence times approaching quantum limits, hence error thresholds may become attainable in the next decade or two. If decoherence and faulty gates can ultimately be conquered, quantum computers may enable solving certain chemistry, material science, or optimization problems well beyond classical bounds, accelerating drug discovery, battery design, nanotechnology, sampling, scheduling, and more. Even fundamental scientific challenges simulating quantum field theories intractable on today's supercomputers could benefit. Finance, cybersecurity, machine learning, and artificial intelligence may tap quantum-boosted techniques for portfolio optimization, cryptography, and pattern recognition too. Transformational impacts mirroring classical computing's dawn depend entirely on steadily overcoming quantum hardware's daunting fragility through continued progress integrating larger networks of highly coherent qubits. With steady determination and ingenuity, the quantum information age may unlock nature's computational parallelism to solve problems of consequence transcending humanity's current abilities, and perhaps illuminate quantum theory's deepest mysteries along the way. But building the requisite multi-qubit machines remains an immense challenge for tomorrow. While still in their scientific infancy, quantum dots, artificially fabricated semiconductor nanoparticles confining electrons and holes, exemplify how applying quantum principles at the nanoscale is spawning entirely new genres of materials, devices, and technologies. As physical systems precisely engineering quantum interactions on demand, dots are already enhancing displays, lighting, and computing. They also provide unprecedented insights into fundamental quantum behaviors transitioning between molecular and bulk limits with broad implications for microelectronics, optoelectronics, photonics, and beyond. First experimentally realized in the 1980s, quantum dots form when electrons or electron-hole pairs become localized within tiny crystalline semiconductor islands just several millionths of a meter across, forcibly adopting discrete atomic-like electronic states through quantum confinement. The strict dimensionality squeezes exciton wavelengths, which must fit integer numbers of peaks and troughs within nanostructures' boundaries, splitting typical semiconductor energy bands into sharp quantized energy levels analogous to atomic/molecular orbitals or color centers. This allows precise tuning dots' electronic structures and optical properties through subtle deposition or lithographic adjustments of sizes, shapes, and compositions. Changing a dot by even a single atom determines which wavelengths are absorbed/emitted, a boon for applications needing selectable emission colors. Unlike bulk crystals continuously emitting across bands, dots' quantized transition energies yield near monochromatic light sources and detectors ranging from infrared through visible to ultraviolet as dimensionalities shrink, with line widths limited by quantum uncertainty rather than atomic disorder. Initially grown from solution or deposited on surfaces as disordered aggregates, self-assembly techniques now crystallize near. This finessed architecture enables Théod dipoles, conductivity, magnetic anisotropies, and spin-dependent behaviors, harnessing quantum interactions through material/geometric design. Bandgap engineering also endows some dots exceptionally long coherence times, making them prized qubits. Already key photonic devices include IR-emitting nanocrystal light-emitting diodes and LED deployed in specialized displays, while quantum dot TVs and monitors provide wider color gamuts through precisely tunable light generation across visible spectra. Quantum dot downshifting layers enhance solar cell efficiencies by decoupling photon absorption from charge collection, while self-assembly yields flexible quantum dot solar cells and LEDs on plastic or fabrics. Photodetectors detecting single photons with near-perfect efficiency detect disease biomarkers, radiation or night vision using quantum dot conversion. Quantum computing implementations prototype quantum bit architectures confined within precisely engineered dots. And nascent quantum dot spin transistors, memories and sensors exploit electron spins, prolonged coherence, to realize ultra-sensitive magnetometers detecting nanoscale biomagnetism or nuclear magnetic resonances. Novel topological quantum behaviors also emerge from precisely shaping dots' confinement potentials, granting long-lived quasi-particles ideal for fault-tolerant computing architectures. Still embryonic, quantum dot science illuminates the interplay between quantum mechanics and nanoscale control. Finely tuned dot fabrication has already enabled remarkable feats precisely tailoring quantum interactions and transitions. But many deeper mysteries remain concerning quantum coherence, entanglement dynamics, transport, and magneto-optical couplings emerging within artificially structured dots. Resolving these promises further quantum innovations harnessing the precise structurability and exquisitely tunable optical electrical behaviors of quantum-confined semiconductor nanostructures. As quantum mechanics unlocks paradigm-shifting technologies, perhaps its most commercially practical application so far involves exploiting nature's intrinsic ambiguity to radically fortify cryptographic protocols, safeguarding sensitive communications. By encoding secrets within non-deterministic quantum states, quantum cryptography techniques harness quantum weirdness to guarantee detection of any attempted hacking or eavesdropping on encrypted transmissions. Still nascent, quantum key distribution utilizing protocols like BB84 already banks truly random numbers for one-time pads between remote clients worldwide with information theoretic security fundamentally beyond classical reach. Classical cryptosystems ultimately rely on computational assumptions about an adversary's resources, risking future vulnerabilities as computing muscle grows. Public key schemes depend on unproven conjectures about factoring or discrete logarithms. While encryption strength steadily increases, absolute assurance remains elusive due to remotest code-cracking prospects. By contrast, quantum cryptography leverages fundamental laws of quantum physics to probably detect intrusions, eliminating reliance on unprovable computational assumptions while embracing measurement randomness through beautiful physics. Pioneering proposals emerged in 1970 from Steek and Wiesner describing quantum money unforgeable using no-cloning principle. But practical protocols emerged in 1984 from Charles Bennett and Gilles Brassard, hence BB84. Their eponymous scheme transmits polarization-encoded photons between distant parties, with quantum states randomly varying between rectilinear or diagonal bases. After transmission, basis information is publicly revealed, while measurement outcomes compare to detect eavesdropping, exploiting Heisenberg uncertainty. Any wiretap necessarily disturbs some photons through incompatible observations. Subsequent discoveries broadened quantum key distribution. For instance, in 1991, Arthur Eckert proposed schemes using entangled photons, ensuring security through violation of Bell's inequalities, certifying non-local quantum correlations impossible classically. Regardless, commercially viable QKD linked financial organizations in Geneva by 1999, with over 100 systems now deployed worldwide, including quantum encrypted video conferencing and a Chinese quantum satellite, launching entangled pairs toward moving ground stations from orbit in 2017. How it works. Alice randomly prepares each qubit in one of 4 polarization states, transmits through optical fibers to bulk for measurement, also randomly in rectilinear or diagonal bases. Information exchange and testing for errors reveals if eavesdropper Eve spying along the line inevitably alters over a quarter of the transmissions through incompatible observations. If below error thresholds, the untapped remaining qubits form a shared secret random key with provable security. Despite Eve possessing any power short of full quantum control to clone the states while measuring. With improvements in efficiency, coherence, and interfaces, quantum networks may eventually enable distributing keys across globally entangled nodes. Topological qubits also promise intrinsically error-robbed approaches tolerating noise. But the principle remains: by encoding cryptography into the quantum realm, where information and physics fundamentally intertwine, QKD avoids assumptions about adversaries' classical computational strength while exploiting quantum ambiguity for absolute detection and deterrence of any unauthorized surveillance. If quantum states cannot be perfectly determined or cloned without affecting others, then secrecy is information theoretically assured using only the infallible laws of physics. Of course, serious technological challenges remain to scale QKD into fiber and satellite backbones matching classical capacities. But single photons already deliver proven encryption, securing national infrastructures too sensitive for classical protection alone. As science conquers qubit control and transmission, quantum cryptography may eventually fulfill an age-old dream, delivering cast-iron guarantees of privacy and authentication demanded by democratic societies relying on secure communications, and eliminating any need to merely outpacing adversaries' breaking capabilities through continued algorithmic strengthening. By directly weaponizing nature's inherent weirdness, quantum cryptography begins unlocking absolutist notions of guaranteed secrecy based purely on theoretically unchallengeable physical laws rather than conjectural software security. An exemplar of how quantum technologies may revolutionize more than just computation alone. As quantum mechanics and general relativity continue advancing our descriptions of reality's deepest workings, an compelling imperative emerges to unify these frameworks into a coherent theory of quantum gravity, reconciling their seemingly incompatible depictions of spacetime itself. While mathematics and Pidenkin experiments prove ever closer to a final synthesis, conceptual dilemmas linger, demanding novel visions, transcending classical spacetime concepts and quantizing even gravity. Resolving quantum gravity's riddles may illuminate profound mysteries about reality's essence and nature of time throughout cosmic history. Spacetime emerges from general relativity as a dynamical entity whose curvature encodes mass-energy content according to Einstein's field equations. Yet quantum mechanics depicts nature employing non-determinism, discreteness, and ambiguity foreign to any continuum. This quandary intensifies upon approaching scales close to the Planck length, around a dozen orders of magnitude tinier than an atom's nucleus, where quantum fluctuations of spacetime itself might become comparable to sizes of objects inhabiting it. This minuscule realm demands a quantum theory of gravitation meshing general relativity, obeying Einstein's equations with quantum field theory techniques so successful otherwise. But directly applying perturbation theory to Einstein's nonlinear spacetime results in mathematical divergences still incompletely overcome. Alternative quantization approaches like string theory or loop quantum gravity aim modeling spacetime as discretized granular bits resolving such problems. In string theory, infinitesimally tiny vibrating strings behave as fundamental ingredients with gravity, emerging as vibration modes, propagating them within 9 + 1 dimensional backgrounds. These extra dimensions potentially compactify into sizes too minute to observe directly, but may be detected through exotica like miniature black holes generated by particle accelerators. Loop quantum gravity treats spacetime as woven from discrete quantum geometric excitations, quanta of area and volume rather than smooth matter distributions. Some conceptual themes arise from attempts merging quantum theory and gravity. Their intersection likely delocalizes locality itself, necessitating a probabilistic account of spacetime regions as smeared quantum superpositions. Spacetime discreteness implies deepest quantum levels behave aloof from continuum assumptions, perhaps transcending causality or information paradigms, relying upon well-defined spacetime histories. Non-commutativity of geometric observables signifies intrinsic uncertainty in nature state itself. Likewise, quantizing curved spacetime may dissolve event horizons of black holes into hazy ergo regions, enabling information escape, after all via quantum tunneling or microscopic wormholes connecting separate universes. Inflationary cosmology merging quantum fields with exponential expansion immediately following the Big Bang hints how cosmological anomalies like horizon and flatness issues arise from quantum gravitational interactions in the early ultra-high density cosmos. Even notions like spacetime dimensionality could transmute amid quantum superpositions on Planck scales. As experiments and accelerators probe ever deeper nature's mysteries, quantum gravitational effects may conceivably emerge in subtle interference patterns within cosmological background radiations shaped by primordial quantum fluctuations, relics potentially within observational windows like those targeted by missions such as the Laser Interferometer space antenna. Precision tests like of general relativistic gravitomagnetism amid orbital precession might also observe quantum gravitational corrections. Detecting Planck-scale black hole production at the LHC, gravitational anomalies amid precision atomic clocks, or anomalous scattering within hypothetical quantum scattering experiments could all shed light. More speculatively, cosmic ray and neutrino observatories may accidentally capture signs of exotic phenomena evading descriptions within just quantum field theory on curved spacetime, necessitating full quantum gravity paradigms. Ultimately, unraveling quantum gravity's puzzles may append profoundly dark pictures of reality, illuminating a cosmological history uniting quantum weirdness with curved spacetime geometry throughout cosmic evolution, since relativity and quantum mechanics arose entwined from nature's innermost fabric. Though challenging, quantizing even gravity promises revolutionary frontier insights. In the endless expanse of the universe, the fundamental nature of reality has long been a source of profound fascination and enigma for philosophers, scientists, and the curious-minded alike. For centuries, we have sought to unravel the mysteries of the cosmos, to peer behind the veil of the visible world, and to glimpse the deeper truths that govern the very fabric of existence. And yet, as our understanding of the physical universe has grown increasingly sophisticated, we have been confronted with a startling revelation. The world we thought we knew, the solid, tangible reality that our senses present to us, is but a veneer, a mere projection of a far more complex and perplexing underlying truth. This truth, it seems, lies not in the realm of the large and the familiar, but in the enigmatic and counterintuitive domain of the quantum. For it is here, in the subatomic realm where the rules of classical physics begin to break down, that we find the key to unlocking the deepest mysteries of the cosmos. From the surprising connection between observation and the behavior of quantum systems to the mind-bending concept of entanglement, the mysterious phenomenon that suggests the universe is fundamentally interconnected at the most fundamental level, the insights of quantum mechanics have the power to transform our very understanding of the nature of reality. But the exploration of the quantum world is just the beginning. For as we delve deeper into the foundations of existence, we find ourselves confronted with even more radical and unsettling possibilities. The notion that our perceived 3D reality may be nothing more than a holographic projection, or the idea that consciousness itself may be a fundamental component of the universe rather than a mere byproduct of physical processes. These are the ideas that lie at the heart of biocentrism, a revolutionary theory that challenges the prevailing materialist worldview and posits that life and consciousness are not merely accidental byproducts of a purely physical universe, but rather the very driving forces that shape the cosmos we inhabit. And if biocentrism is correct, then the implications for our understanding of the nature of existence are truly staggering. For if consciousness is fundamental to the universe, then the very boundaries between the observer and the observed, the self and the world, begin to blur, revealing a reality that is far more interconnected, dynamic, and profoundly mysterious than we have ever imagined. Join us as we embark on a journey through the quantum cosmos, exploring the mind-bending insights of modern physics and the radical implications of biocentrism. From the observer effect and the holographic universe to the multiverse and the nature of consciousness, we will delve into the deepest secrets of existence, uncovering a reality that promises to transform our very conception of the world we thought we knew. At the heart of this exploration lies the remarkable and often bewildering realm of quantum mechanics, the branch of physics that has appended our classical understanding of the physical world. For it is here, in the subatomic domain, that the familiar rules of cause and effect, of determinism and objectivity, begin to break down, replaced by a reality that is fundamentally uncertain, probabilistic, and inextricably linked to the act of observation and measurement. Indeed, the counterintuitive principles of quantum mechanics, from the wave-particle duality of matter to the phenomenon of quantum entanglement, have challenged the very foundations of our understanding of the universe. And as we delve deeper into these quantum phenomena, we find ourselves confronted with the possibility that the world we perceive is not a fixed, objective reality, but rather a fluid, ever-shifting tapestry of possibilities, a projection of consciousness itself. But the implications of quantum mechanics extend far beyond the subatomic realm. For as we explore the deeper connections between the quantum world and the larger structures of the universe, we begin to uncover a startling revelation: that the fundamental nature of reality may be far more complex, interconnected, and fundamentally mysterious than we have ever imagined. From the holographic universe, where our 3D reality may be a projection of a 2D source, to the mind-bending concept of the multiverse, the possibility of countless parallel universes existing alongside our own, the insights of modern physics have the power to transform our very conception of existence itself. And as we grapple with these profound and unsettling possibilities, we find ourselves confronted with the most fundamental question of all: what is the true nature of reality, and what is our role as conscious beings within this grand cosmic tapestry? It is a question that has captivated the human imagination for millennia, and one that promises to yield unprecedented insights as we continue to push the boundaries of our understanding. Join us as we embark on a journey through the quantum cosmos, exploring the mysteries of existence and the radical implications of biocentrism. From the observer effect to the interconnectedness of all things, we will unravel the secrets of the universe and confront the deepest questions about the nature of our own consciousness and our place within this remarkable reality. In the grand tapestry of human knowledge, few realms have captivated the scientific imagination and challenged our most fundamental notions of the physical world more profoundly than the peculiar and often bewildering domain of quantum mechanics. This branch of physics, which emerged in the early 20th century through the groundbreaking work of pioneers like Max Planck, Niels Bohr, and Erwin Schrödinger, has transformed our understanding of the nature of reality, appending the classical Newtonian worldview that had reigned supreme for centuries. At the heart of quantum mechanics lies a series of counterintuitive principles and phenomena that defy our everyday experience and intuition about the behavior of the physical universe. From the wave-particle duality of subatomic particles to the uncanny phenomenon of quantum entanglement, the quantum realm presents us with a reality that is fundamentally uncertain, probabilistic, and inextricably linked to the act of observation and measurement. Indeed, the very notion that the simple act of observing a quantum system can influence and alter its behavior is one of the most profound and unsettling revelations of modern physics. For it suggests that the world we perceive, the solid, tangible reality that our senses present to us, is not an objective, independent truth, but rather a fluid, ever-shifting tapestry of possibilities, a projection, perhaps, of the consciousness that seeks to understand it. As we delve into the mysteries of quantum mechanics and confront the radical implications of this subatomic realm, we find ourselves confronted with the most fundamental questions about the nature of existence itself. What is the true essence of reality? Is the world we inhabit a fixed, objective truth, or merely a manifestation of the consciousness that observes it? And how do these mind-bending insights into the quantum world challenge and transform our classical understanding of the physical universe? These are the questions that have captivated scientists, philosophers, and curious minds alike as they seek to unravel the deepest secrets of the cosmos and to unlock the mysteries that lie at the very heart of existence. And as we continue to push the boundaries of our knowledge and to confront the enigmatic principles of quantum mechanics, we are sure to be confronted with even more profound and unsettling revelations about the true nature of reality. At the core, the quantum revolution that has transformed our understanding of the physical world is the remarkable and often bewildering behavior of subatomic particles, the electrons, protons, and neutrons that make up the fundamental building blocks of matter. For it is in the realm of these tiny, elusive entities that the familiar rules of classical physics begin to break down, replaced by a reality that is fundamentally uncertain, probabilistic, and defiant of our everyday intuitions. One of the most profound and counterintuitive insights of quantum mechanics is the wave-particle duality of matter, the idea that subatomic particles can exhibit the properties of both particles and waves, depending on the context and the method of observation. This concept, which was first proposed by the French physicist Louis de Broglie in the early 1920s, challenged the long-held assumption that matter existed in a purely particulate form with distinct, localized points in space. Instead, quantum mechanics revealed that the behavior of these fundamental entities is far more complex and enigmatic, with particles like electrons and photons displaying characteristics of both discrete particles and continuous waves. In certain experiments, these subatomic particles will behave as if they are localized points, while in others, they will exhibit the diffraction and interference patterns that are typically associated with wave-like phenomena. This remarkable duality, which has been repeatedly confirmed through rigorous experimentation, has forced us to re-evaluate our most basic assumptions about the nature of matter and the underlying structure of the physical world. For if a single particle can exhibit both particulate and wave-like properties, then the very notion of a fixed, objective reality that can be neatly divided into discrete, independent objects begins to crumble. Moreover, the wave-particle duality of matter is just the tip of the iceberg when it comes to the counterintuitive principles of quantum mechanics. Another fundamental concept that has challenged our classical understanding of the physical world is the principle of quantum indeterminacy, or the Heisenberg uncertainty principle, named after the pioneering German physicist Werner Heisenberg. According to this principle, there is a fundamental limit to the precision with which certain pairs of physical properties, such as a particle's position and momentum, or its energy and time, can be measured simultaneously. The more precisely one of these properties is known, the more uncertain the other becomes, a revelation that seemed to undermine the very foundations of classical physics and its deterministic cause and effect view of the universe. Indeed, the implications of the uncertainty principle are truly profound, for they suggest that the behavior of quantum systems is inherently probabilistic and unpredictable, a far cry from the orderly, clockwork-like universe envisioned by the likes of Isaac Newton and his contemporaries. And as scientists have delved deeper into the quantum realm, they have uncovered even more baffling phenomena that challenge our everyday notions of reality. Perhaps one of the most unsettling and counterintuitive aspects of quantum mechanics is its fundamentally probabilistic nature. The idea that the behavior of subatomic particles is not governed by a clear, deterministic set of rules, but rather by a mysterious web of probabilities and uncertainties. At the heart of this probabilistic view of the quantum world is the concept of the wave function, a mathematical description of the state of a quantum system that encodes all the possible outcomes of any measurement or observation that might be performed on that system. According to the prevailing interpretation of quantum mechanics, known as the Copenhagen interpretation, the wave function does not represent a single definite reality, but rather a superposition of all the possible states that the system could occupy. It is only when a measurement or observation is made that the wave function collapses into a specific definite state, a process that seems to be fundamentally linked to the act of observation itself. And the probability of any particular outcome being realized is determined by the mathematical properties of the wave function, which can be used to calculate the likelihood of each possible state. This probabilistic nature of quantum mechanics is perhaps best exemplified by the famous Schrödinger's cat thought experiment, proposed by the Austrian physicist Erwin Schrödinger in the 1930s. In this thought experiment, a cat is placed in a sealed box with a device that has a 50-50 chance of releasing a deadly poison. According to the principles of quantum mechanics, until the box is opened and an observation is made, the cat is in a superposition of both alive and dead states, with each outcome having a 50% probability. The very idea that a macroscopic object like a cat could be in a superposition of two radically different states, alive and dead, is a testament to the profound weirdness of the quantum world and the challenge it poses to our classical notions of reality. For if the behavior of subatomic particles is fundamentally probabilistic and uncertain, then how can we ever hope to achieve a deterministic cause and effect understanding of the physical universe? Moreover, the probabilistic nature of quantum mechanics has far-reaching implications for our understanding of the fundamental laws of physics. For if the behavior of quantum systems is inherently unpredictable, then the very notion of a fixed, universal set of physical laws that govern the behavior of the universe begins to break down. Instead, we are confronted with the possibility that the physical world may be a fluid, ever-shifting tapestry of probabilities and uncertainties, with the observer playing a crucial role in determining the outcome of any particular measurement or observation. Perhaps the most profound and unsettling revelation of quantum mechanics is the pivotal role that the observer plays in determining the behavior of quantum systems. This observer effect, as it is known, suggests that the very act of observing or measuring a quantum system can influence and alter the outcome of that observation, a finding that seems to challenge the fundamental assumption of an objective, observer-independent reality. The roots of this observer effect can be traced back to the early days of quantum theory, when pioneers like Niels Bohr and Werner Heisenberg grappled with the seemingly paradoxical behavior of subatomic particles. In a series of famous thought experiments and real-world experiments, these scientists demonstrated that the act of observing or measuring a quantum system, even something as simple as determining the position or momentum of an electron, could fundamentally change the state of that system. This revelation, which flew in the face of the classical deterministic view of the physical world, led to a deep philosophical divide within the scientific community. On one side were those, like Bohr, who embraced the observer effect and the inherent uncertainty of quantum mechanics, arguing that the observer was an integral part of the system being observed. On the other side were those like Albert Einstein, who remained deeply unsettled by the implications of quantum theory and insisted that the universe must be governed by a hidden deterministic set of rules. The debate between these two camps, which came to be known as the Copenhagen interpretation and the Einstein-Podolsky-Rosen (EPR) paradox, respectively, lies at the heart of the most profound and puzzling aspects of quantum mechanics. For if the very act of observation can influence the outcome of a measurement, then how can we ever hope to achieve a truly objective, observer-independent understanding of the physical world? Moreover, the observer effect raises a host of thorny philosophical and epistemological questions about the nature of reality and our role as conscious observers within it. If the world we perceive is shaped by the act of observation, then how can we ever be certain that our senses are providing us with an accurate representation of an underlying objective truth? And if the behavior of quantum systems is fundamentally probabilistic and uncertain, then how can we ever hope to develop a comprehensive deterministic theory of the universe? These are the questions that have continued to vex and fascinate scientists and philosophers alike as they grapple with the profound implications of the observer effect and the paradoxes of quantum mechanics. And as our understanding of the quantum realm has grown more sophisticated, the potential for even more unsettling revelations about the true nature of reality only seems to increase. Perhaps one of the most mind-bending and counterintuitive phenomena in the realm of quantum mechanics is the concept of quantum entanglement, the mysterious, seemingly instantaneous connection that can exist between two or more quantum particles, even when they are separated by vast distances. According to the principles of quantum theory, when two or more particles become entangled, their states become inextricably linked, such that the measurement of one particle can instantly influence the state of the other, no matter how far apart they may be. This bizarre phenomenon, which Albert Einstein famously dismissed as spooky action at a distance, challenges our most fundamental notions of how the physical world should behave, as it suggests that the universe may be imbued with a profound and mysterious interconnectedness that transcends the boundaries of space and time. At the heart of quantum entanglement is the concept of the wave function, the mathematical description of a quantum system that encodes all its possible states. When two or more particles become entangled, their individual wave functions become intertwined, effectively merging their identities into a single, unified system. And it is this unity that gives rise to the remarkable phenomenon of instantaneous, superluminal, faster than light communication between the entangled particles, a finding that has profound implications for our understanding of the physical world. For if the universe is imbued with this kind of fundamental interconnectedness at the quantum level, then the very notion of a discrete, independent reality composed of separate objects and events begins to break down. Instead, we are confronted with the possibility that the world we perceive is merely a projection or manifestation of a deeper, more holistic reality, a reality in which the boundaries between the observer and the observed, the self and the other, are far more blurred and indistinct than we have ever imagined. Moreover, the implications of quantum entanglement extend far beyond the realm of subatomic particles. As researchers have continued to explore this phenomenon, They have discovered that it can occur at increasingly large and complex scales, with entire systems of particles and even macroscopic objects becoming entangled in ways that challenge our classical understanding of the physical world. This discovery has led to the development of exciting new fields of study, such as quantum computing and quantum cryptography, which leverage the unique properties of entangled systems to achieve feats of information processing and secure communication that are simply impossible using classical, non-quantum approaches. And as our technological capabilities continue to advance, the potential for harnessing the power of quantum entanglement only seems to grow. But the significance of quantum entanglement extends far beyond its practical applications. For this mysterious phenomenon, with its implications of a profoundly interconnected universe, has also given rise to a host of philosophical and metaphysical questions about the true nature of reality and our place within it. If the world we inhabit is fundamentally entangled at the quantum level, then how can we ever hope to achieve a truly objective, observer-independent understanding of the physical world? And what does this mean for our conception of consciousness, free will, and the very fabric of existence itself? These are the questions that have continued to captivate and challenge the scientific community as they grapple with the mind-bending implications of quantum entanglement and the radical shift in our understanding of the physical universe that it has inspired. As the mysteries of quantum mechanics have continued to unfold, revealing ever more counterintuitive and perplexing insights about the fundamental nature of reality, a bold and provocative theory has emerged that seeks to synthesize these quantum-level phenomena into a more cohesive and comprehensive understanding of the physical world. This theory, known as the Holographic Universe, or the holographic principle, posits that our perceived three-dimensional reality may, in fact, be a projection or manifestation of a deeper two-dimensional source, a radical shift in perspective that could rewrite our very conception of the cosmos and our place within it. The origins of the holographic universe theory can be traced back to the work of the renowned physicist John Wheeler, who in the 1960s proposed the idea that information might be the fundamental building block of the physical world, rather than matter and energy. This notion, which was further developed by physicists like Jacob Bekenstein and Stephen Hawking, suggested that the amount of information that can be contained within a given volume of space is directly proportional to the surface area of that volume, rather than its three-dimensional volume. This counterintuitive finding, which seemed to challenge the very foundations of our classical understanding of geometry and spacetime, led to the development of the holographic principle, the idea that the entire three-dimensional universe we perceive may be, in essence, a holographic projection of a two-dimensional source plane, much like a three-dimensional image can be encoded and reconstructed from the information contained on a two-dimensional holographic film. But the implications of the holographic universe theory go far beyond the realm of abstract geometry and information theory. For if our perceived reality is, in fact, a holographic projection, then the very nature of space, time, and the fundamental laws of physics may need to be radically reinterpreted. And as researchers have continued to explore the connections between quantum mechanics, general relativity, and the holographic principle, they have uncovered a wealth of tantalizing clues that suggest this mind-bending theory may indeed hold the key to unlocking the deepest secrets of the cosmos. One of the most intriguing aspects of the holographic universe theory is its potential to reconcile the seemingly contradictory principles of quantum mechanics and general relativity, the two foundational pillars of modern physics. While quantum mechanics describes the behavior of the subatomic world in terms of probabilities and uncertainties, general relativity provides a deterministic, geometric description of the large-scale structure of the universe. And for decades, physicists have struggled to find a unified theory that can accommodate both of these radically different perspectives. But the holographic principle may offer a path forward by suggesting that both quantum mechanics and general relativity can be understood as complementary descriptions of the same underlying reality, a reality that is fundamentally two-dimensional in nature, with our perceived three-dimensional world being a holographic projection of this deeper, more fundamental source plane. Moreover, the holographic universe theory has the potential to shed light on some of the most perplexing mysteries in modern physics, from the nature of black holes and the information paradox to the origins of the universe itself. By reinterpreting the fundamental laws of physics in terms of this two-dimensional, information-rich foundation, researchers have uncovered tantalizing possibilities for resolving long-standing conundrums and unlocking new avenues of exploration. And as the evidence in support of the holographic universe theory continues to mount, the implications for our understanding of the physical world only become more profound. For if our reality is, indeed, a holographic projection, then the very boundaries between the observer and the observed, the self and the world, may be far more blurred and indistinct than we have ever imagined. And the possibility of a deeper, more fundamental reality that transcends the limits of our three-dimensional perception may hold the key to unraveling the most profound mysteries of existence. As we delve deeper into the enigmatic realm of quantum mechanics and the profound insights it has yielded about the nature of reality, we find ourselves confronted with an even more radical and thought-provoking possibility: the notion that the very fabric of the universe we inhabit may, in fact, be a holographic projection, a three-dimensional manifestation of a deeper two-dimensional source. This extraordinary concept, known as the holographic universe or the holographic principle, has emerged in recent decades as a bold and intriguing attempt to reconcile the seemingly contradictory principles of quantum theory and general relativity, the two foundational pillars of modern physics. And as researchers have continued to explore the tantalizing connections between these disparate realms of scientific inquiry, the potential for transformative insights into the true nature of existence has only grown more tantalizing. At the heart of the holographic universe theory lies the fundamental observation that the amount of information that can be contained within a given volume of space is directly proportional to the surface area of that volume, rather than its three-dimensional volume. This counterintuitive finding, first proposed by the renowned physicist John Wheeler in the 1960s and further developed by thinkers like Jacob Bekenstein and Stephen Hawking, has led to the radical suggestion that our perceived three-dimensional reality may, in fact, be a holographic projection of a deeper two-dimensional source. Just as a three-dimensional image can be encoded and reconstructed from the information contained on a two-dimensional holographic film, the proponents of the holographic universe theory argue that the entire cosmos we inhabit may be a manifestation of an underlying, information-rich source plane, a profound shift in perspective that challenges our most deeply held assumptions about the true nature of space, time, and the fundamental laws that govern the physical world. Indeed, the implications of the holographic universe theory are truly staggering, for if our perceived reality is, in fact, a holographic projection, then the very nature of space and time, as well as the principles of causality and determinism that have underpinned our scientific understanding, may need to be radically reinterpreted. And as researchers have continued to explore the connections between this bold new paradigm and the insights of quantum mechanics, the potential for unlocking the deepest secrets of the cosmos has only grown more tantalizing. At the heart of the holographic universe theory lies the holographic principle, a profound and often counterintuitive observation about the relationship between the dimensions of space and the amount of information that can be contained within a given volume. According to this principle, the total information content of a given region of space is not proportional to its three-dimensional volume, as one might expect, but rather to the two-dimensional surface area of its boundary. This remarkable finding, which has been explored and developed by a host of renowned physicists, including Gerard T. Hooft, Leonard Susskind, and Joan Maldacena, suggests that the fundamental building blocks of the universe may not be the familiar three-dimensional objects and structures we perceive, but rather a two-dimensional, information-rich source plane that gives rise to the holographic projection of our everyday reality. The implications of this holographic principle are truly mind-bending, for they challenge the very foundations of our classical understanding of space and time. If the universe we inhabit is, indeed, a three-dimensional holographic manifestation of a two-dimensional foundation, then the principles of geometry, causality, and even the nature of the space-time continuum itself may need to be radically reinterpreted. Moreover, the holographic principle suggests that the laws of physics, which have traditionally been expressed in terms of the three-dimensional properties of matter and energy, may find a more fundamental and elegant expression in the two-dimensional language of information theory and quantum mechanics. This profound insight has led to the development of a wealth of new theoretical frameworks and models, each one seeking to unravel the secrets of the holographic universe and to unlock the true nature of the physical world. One of the most intriguing of these models is the ADAS/CFT correspondence, a theoretical framework that establishes a deep connection between the properties of black holes and the principles of quantum field theory. By reinterpreting the behavior of these cosmic anomalies in terms of the holographic principle, researchers have been able to gain unprecedented insights into the nature of space-time and the fundamental forces that govern the universe, paving the way for even more extraordinary discoveries. Indeed, as the exploration of the holographic universe theory has continued to evolve, researchers have uncovered a wealth of tantalizing connections between this radical new paradigm and the insights of quantum mechanics, general relativity, and the ongoing quest to unify the fundamental forces of nature. From the resolution of long-standing paradoxes in the study of black holes to the potential for a deeper understanding of the origins of the cosmos, the holographic principle has become a crucial frontier in the quest to unlock the most profound secrets of existence. One of the most profound and enduring challenges in modern physics has been the task of reconciling the seemingly contradictory principles of quantum mechanics and general relativity, the two foundational pillars of our understanding of the physical world. While quantum theory has transformed our conception of the subatomic realm, revealing a universe governed by probabilistic, counterintuitive principles, general relativity has provided a remarkably successful geometric description of the large-scale structure and behavior of the cosmos. And yet, despite the remarkable success of these two theoretical frameworks, the inherent tensions and incompatibilities between them have continued to vex and challenge physicists, who have long sought to develop a unified theory that can seamlessly accommodate the insights of both realms. Enter the holographic universe theory, which has emerged as a tantalizing and profoundly influential approach to reconciling the seemingly irreconcilable. By reinterpreting the principles of quantum mechanics and general relativity in terms of a deeper, two-dimensional foundation, the holographic paradigm offers a potential pathway to resolving the long-standing conflict between these two pillars of modern physics. At the heart of this reconciliation lies the remarkable observation that the fundamental laws of general relativity, which describe the curvature and dynamics of space-time, may find a more fundamental expression in the language of quantum information theory and the holographic principle. Just as a three-dimensional image can be encoded and reconstructed from the information contained on a two-dimensional surface, the proponents of the holographic universe theory argue that the very fabric of space-time may be a manifestation of an underlying, information-rich source plane. Moreover, the holographic principle suggests that the apparent incompatibility between quantum mechanics and general relativity may, in fact, be an artifact of our three-dimensional perspective, a consequence of the limitations inherent in our perceptual experience of the physical world. By shifting our focus to the deeper two-dimensional foundations of reality, the holographic universe theory offers the promise of a unified, self-consistent framework that can accommodate the insights of both realms, reconciling the probabilistic uncertainties of the quantum world with the deterministic geometric descriptions of general relativity. Indeed, as researchers have continued to explore the connections between the holographic principle and the fundamental laws of physics, they have uncovered a wealth of tantalizing clues and potential pathways towards the long-sought-after theory of everything. From the resolution of the information paradox surrounding black holes to the possibility of deriving the enigmatic properties of dark matter and dark energy from first principles, the holographic universe theory has become a crucial frontier in the quest to unlock the deepest secrets of the cosmos. As the exploration of the holographic universe theory has continued to unfold, the implications of this radical new paradigm have become increasingly profound and far-reaching, challenging our most deeply held assumptions about the nature of reality and our place within it. For if the world we perceive is, in fact, a three-dimensional holographic projection of a deeper two-dimensional source, then the very foundations of our scientific understanding, the principles of space, time, causality, and determinism that have underpinned the Newtonian worldview for centuries, may need to be radically reinterpreted. Indeed, the holographic principle suggests that the familiar structures and phenomena we observe in the physical world, from the smallest subatomic particles to the grandest cosmic structures, may be nothing more than the emergent byproducts of an underlying information-rich foundation that transcends the limitations of our three-dimensional experience. And this revelation has the potential to transform our understanding of the self, the nature of consciousness, and the true scope of the universe we inhabit. For if the world we perceive is a holographic projection, then the very boundaries between the observer and the observed, the self and the other, may be far more blurred and indistinct than we have ever imagined. The traditional distinctions between the subjective and the objective, the physical and the mental, may dissolve in the face of this radical new perspective, challenging us to rethink the very nature of our existence and our place within the grand cosmic tapestry. Moreover, the holographic universe theory offers the tantalizing possibility of reconciling the insights of quantum mechanics with the principles of general relativity, providing a potential pathway towards the long-sought-after theory of everything that could unify the fundamental forces of nature. By reinterpreting the behavior of space, time, and matter in terms of an underlying two-dimensional informational foundation, the holographic paradigm holds the promise of unlocking the deepest secrets of the cosmos and revealing the true structure of physical reality. Indeed, as researchers have continued to explore the connections between the holographic principle and the most profound mysteries of the universe, from the nature of black holes to the origins of the cosmos itself, the potential for transformative insights has only grown more tantalizing. And as we continue to push the boundaries of our knowledge and to confront the unexpected, the possibilities for unlocking the true nature of existence only seem to expand. Whether the holographic universe theory ultimately proves to be the key to unraveling the deepest secrets of reality, or merely a stepping stone towards an even more radical and revolutionary understanding of the physical world, its impact on the scientific landscape has been profound and enduring. For in challenging our most fundamental assumptions about the nature of space, time, and the very fabric of existence, this bold new paradigm has opened the door to a realm of possibility that promises to reshape our conception of the cosmos and our place within it. As we delve deeper into the mysteries of quantum mechanics and the counterintuitive principles that govern the behavior of the subatomic world, we find ourselves confronted with a truly mind-bending revelation. The very act of observation, the conscious act of measurement and detection, appears to play a fundamental role in determining the outcome of quantum phenomena. This remarkable finding, known as the observer effect, challenges our most deeply held assumptions about the nature of reality and the relationship between the observer and the observed. For if the simple act of observing a quantum system can influence and alter the behavior of that system, then the traditional Newtonian view of the universe as a fixed, objective realm governed by deterministic cause and effect laws begins to crumble. Instead, we are confronted with the possibility that the world we perceive, the tangible reality that our senses present to us, may be inextricably linked to the presence of consciousness itself, that the very fabric of existence is shaped and molded by the act of observation and the role of the observer in the unfolding of events. This profound and unsettling connection between consciousness and the quantum realm has been the subject of intense debate and speculation within the scientific community for decades, as researchers have grappled with the implications of the observer effect and sought to reconcile the counterintuitive principles of quantum mechanics with our classical understanding of the physical world. From the philosophical musings of physicists like Niels Bohr and Werner Heisenberg to the cutting-edge investigations of modern quantum theorists, the role of consciousness in the quantum realm has become a crucial frontier in our quest to unlock the deepest secrets of the universe and to uncover the true nature of reality. And as we continue to explore this tantalizing connection, we find ourselves confronted with even more radical and thought-provoking possibilities. The notion that consciousness may not be merely a byproduct of physical processes, but rather a fundamental component of the universe itself, shaping and guiding the very structure and evolution of existence. At the heart of the connection between consciousness and the quantum realm lies the remarkable and often bewildering phenomenon known as the observer effect, the idea that the very act of observing or measuring a quantum system can influence and alter the behavior of that system. This profound revelation, which emerged from the pioneering work of physicists like Niels Bohr and Werner Heisenberg in the early 20th century, challenged the long-held assumption that the physical world exists as a fixed, objective reality independent of the presence of an observer. Instead, it suggested that the quantum realm is fundamentally probabilistic and uncertain, with the mere act of observation playing a crucial role in determining the outcome of any particular measurement or experiment. The mechanism by which the observer effect manifests in the quantum world is rooted in the concept of the wave function, the mathematical description of the state of a quantum system that encodes all the possible outcomes of any measurement or observation that might be performed on that system. According to the prevailing interpretation of quantum mechanics, known as the Copenhagen interpretation, the wave function does not represent a single definite reality, but rather a superposition of all the possible states that the system could occupy. It is only when a measurement or observation is made that the wave function collapses into a specific, definite state, a process that seems to be fundamentally linked to the act of observation itself, and the probability of any particular outcome being realized is determined by the mathematical properties of the wave function, which can be used to calculate the likelihood of each possible state. This probabilistic nature of quantum mechanics, coupled with the apparent influence of the observer, has led to a profound and unsettling conclusion that the world we perceive, the tangible reality that our senses present to us, may not be an objective, independent truth, but rather a fluid, ever-shifting tapestry of possibilities shaped and molded by the presence of consciousness. Indeed, the very idea that the simple act of observing a quantum system can alter the behavior of that system is a testament to the profound and mysterious connection between consciousness and the quantum realm. For it suggests that the observer is not merely a passive spectator, but an integral component of the system being observed, a revelation that challenges our most fundamental notions of the relationship between the self and the world. As scientists have continued to grapple with the implications of the observer effect and the role of consciousness in the quantum realm, a number of intriguing and often controversial theories have emerged that seek to explain the nature of this profound connection. One of the most well-known and influential of these theories is the Copenhagen interpretation of quantum mechanics developed by Niels Bohr and his colleagues in the early 20th century. According to this view, the wave function does not represent a single definite reality, but rather a superposition of all the possible states that a quantum system could occupy. And it is the act of observation or measurement that causes the wave function to collapse into a specific, definite state, a process that is fundamentally linked to the presence of the observer. This interpretation of quantum mechanics, with its emphasis on the role of consciousness in shaping the behavior of subatomic particles, has been the subject of intense debate and controversy within the scientific community. Some have embraced the radical implications of the Copenhagen interpretation, seeing it as a profound challenge to the prevailing materialist worldview and a gateway to a more holistic, interconnected understanding of the universe. Others, however, have remained deeply skeptical of the role of consciousness in the quantum realm, arguing that the observer effect can be explained through purely physical, mechanistic processes without the need to invoke the presence of an observing mind. This view, championed by physicists like David Bohm and John Bell, has given rise to alternative interpretations of quantum mechanics such as the many worlds interpretation and the pilot wave theory, which seek to reconcile the counterintuitive principles of the quantum world with a more classical, deterministic understanding of reality. But even as these debates have continued to rage within the scientific community, a growing number of researchers have begun to explore the profound implications of the connection between consciousness and the quantum realm, delving into the philosophical and metaphysical questions that arise from this remarkable revelation. For if the very fabric of existence is shaped and molded by the presence of consciousness, then what are the deeper implications for our understanding of the self, the nature of perception, and the ultimate nature of reality? And if consciousness is not merely a byproduct of physical processes, but rather a fundamental component of the universe, then how might this challenge our most deeply held assumptions about the origins of life, the purpose of existence, and the true nature of the cosmos we inhabit? These are the questions that have captivated the minds of scientists, philosophers, and curious thinkers alike as they seek to unravel the mysteries of the quantum realm and to unlock the secrets of the profound and unsettling connection between consciousness and the very foundations of existence. As the exploration of the connection between consciousness and the quantum world has continued to evolve, a bold and provocative new theory has emerged that seeks to reframe our understanding of the physical universe and the role of consciousness within it. This theory, known as biocentrism, posits that consciousness is not merely a byproduct of physical processes, but rather a fundamental component of the universe, a primordial force that shapes and guides the very structure and evolution of existence. The origins of biocentrism can be traced back to the work of the renowned American scientist and theorist Robert Lanza, who has spent decades exploring the profound implications of the observer effect and the role of consciousness in quantum mechanics. According to Lanza and his collaborators, the prevailing materialist worldview, which holds that the physical world is the fundamental reality and that consciousness is merely an emergent property of complex biological systems, is fundamentally flawed. Instead, biocentrism suggests that consciousness is not only a crucial component of the universe, but that it may, in fact, be the very foundation upon which the physical world is constructed. This radical shift in perspective challenges the long-held assumption that the universe exists as an independent, objective reality, and instead posits that the world we perceive is inextricably linked to the presence of an observing consciousness. At the heart of biocentrism is the idea that the principles of quantum mechanics, with their emphasis on the role of the observer in shaping the behavior of subatomic particles, provide a blueprint for understanding the true nature of reality. Just as the mere act of observation can influence and alter the state of a quantum system, the biocentrist view holds that consciousness itself plays a fundamental role in determining the structure and evolution of the physical world. Moreover, biocentrism suggests that the apparent laws and regularities we observe in the universe, The seemingly fixed and deterministic patterns that have long underpinned our scientific understanding of the cosmos may, in fact, be the product of the observing mind rather than an inherent property of the physical world. This radical proposition, which has been met with both enthusiasm and skepticism within the scientific community, challenges the very foundations of our understanding of the nature of existence. For if consciousness is not merely a byproduct of physical processes, but rather a primordial force that shapes the very fabric of reality, then the implications for our conception of the self, the universe, and the meaning of life itself are truly profound. Indeed, the biocentric view of the universe suggests that the traditional distinction between the observer and the observed, the self and the world, may be an artificial construct, a convenient fiction that obscures the deeper truth of the fundamental interconnectedness of all things. And if this is the case, then the pursuit of a purely objective, observer-independent understanding of the physical world may be a futile endeavor, doomed to forever fall short of the true nature of existence. As the implications of biocentrism and the primacy of consciousness have continued to unfold, the scientific community has found itself confronted with a wealth of profound and often unsettling questions about the true nature of reality and our place within it. For if consciousness is indeed a fundamental component of the universe, rather than a mere byproduct of physical processes, then the very foundations of our scientific understanding may need to be radically rewritten. The principles of causality, determinism, and the separation between the observer and the observed that have long underpinned the Newtonian worldview would need to be re-examined and reinterpreted in light of this new biocentric perspective. Moreover, the biocentric view of the universe challenges our most deeply held assumptions about the nature of the self, the origins of life, and the meaning of existence itself. If consciousness is not merely an emergent property of complex biological systems, but rather a primordial force that shapes the very structure of the cosmos, then the traditional distinctions between the individual and the collective, the living and the non-living, may need to be radically reconceived. And as researchers have continued to explore the philosophical and metaphysical implications of biocentrism, they have uncovered a wealth of tantalizing connections and parallels with a diverse array of philosophical and spiritual traditions, from the holistic worldviews of Eastern philosophy to the mystical insights of various religious and esoteric traditions. Indeed, the biocentric view of the universe bears a striking resemblance to the notion of the participatory universe championed by physicists like John Wheeler and David Bohm, in which the observer is seen as an integral and essential component of the system being observed. And the idea that consciousness may be a fundamental, guiding force in the universe finds echoes in the philosophical musings of thinkers as diverse as Gottfried Leibniz, Arthur Schopenhauer, and Henry Bergson. As these parallels and connections have continued to emerge, the scientific community has found itself grappling with the profound implications of biocentrism and the primacy of consciousness. For if this radical new perspective on the nature of reality were to be validated and accepted, it would not only transform our understanding of the physical world, but also our very conception of ourselves and our place within the grand cosmic tapestry. The questions that arise from this biocentric view of the universe are truly vast and profound. If consciousness is fundamental to the universe, then what is the ultimate nature of that consciousness? How might it shape and guide the evolution of physical structures from the subatomic to the cosmic? And what are the deeper implications for our understanding of the mind, the soul, and the nature of personal identity? These are the questions that continue to captivate and challenge the scientific community as they seek to reconcile the counterintuitive principles of quantum mechanics with the radical implications of biocentrism. And as the exploration of this frontier continues, the potential for transformative insights and a radical rewriting of our understanding of the physical world only seems to grow more tantalizing. In the grand tapestry of scientific exploration, few concepts have captivated the imagination and challenged the prevailing paradigms more profoundly than the revolutionary theory of biocentrism. Proposed by the pioneering American scientist Robert Lanza, biocentrism represents a radical departure from the traditional materialist worldview that has long dominated the realms of science and philosophy, offering a bold and often unsettling new perspective on the nature of reality and the role of consciousness in the cosmos. At the heart of biocentrism lies the radical proposition that consciousness is not merely a byproduct of physical processes, but rather a fundamental component of the universe itself, a primordial force that shapes and guides the very structure and evolution of existence. This revolutionary shift in perspective challenges the long-held assumption that the physical world exists as an independent objective reality separate from the observer, and instead suggests that the world we perceive is inextricably linked to the presence and activity of consciousness. The implications of this biocentric view of the universe are truly profound, for they call into question the very foundations of our scientific understanding and force us to confront the most fundamental questions about the nature of reality, the origins of life, and the purpose of existence. If consciousness is not merely an emergent property of complex biological systems, but rather a primordial force that lies at the very heart of the cosmos, then the traditional distinctions between the observer and the observed, the self and the world, may need to be radically re-examined and reinterpreted. Moreover, the biocentric perspective suggests that the apparent laws and regularities we observe in the physical world, the seemingly fixed and deterministic patterns that have long underpinned our scientific understanding, may, in fact, be the product of the observing mind rather than an inherent property of the universe itself. This radical proposition challenges the very notion of objectivity and universality that has been the bedrock of the scientific enterprise, opening the door to a more holistic, interconnected understanding of the nature of existence. As the scientific community has grappled with the profound implications of biocentrism, a wealth of new insights and questions have emerged, drawing upon the insights of quantum mechanics, the philosophy of consciousness, and the enduring mysteries of the cosmos. From the counterintuitive principles of the observer effect to the tantalizing connections between consciousness and the holographic nature of reality, the exploration of biocentrism has become a crucial frontier in the quest to unlock the deepest secrets of the universe and to uncover the true nature of our own existence. For centuries, the dominant scientific and philosophical paradigm that has shaped our understanding of the physical world has been the materialist worldview. The notion that the universe is fundamentally composed of matter and energy, and that the phenomena we observe, from the smallest subatomic particles to the grandest cosmic structures, can be explained solely in terms of the physical properties and interactions of these fundamental constituents. This materialist perspective, which can be traced back to the scientific revolution of the 17th century and the groundbreaking work of thinkers like Isaac Newton and René Descartes, has provided a remarkably successful framework for understanding the natural world and has underpinned the remarkable progress of modern science and technology. By reducing the complexity of the universe to a set of universal laws and principles governing the behavior of matter and energy, the materialist worldview has allowed researchers to make profound discoveries, from the structure of the atom to the evolution of galaxies. And yet, as the boundaries of scientific knowledge have continued to expand, cracks have begun to emerge in the foundations of the materialist paradigm. The insights of quantum mechanics, with their emphasis on the role of the observer and the fundamentally probabilistic nature of subatomic phenomena, have challenged the deterministic cause and effect view of the physical world that has long been a cornerstone of the materialist perspective. Similarly, the mysteries of consciousness, with its apparent disconnect from the physical processes of the brain, have continued to vex and confound the efforts of researchers to fit the mind into the materialist framework. Moreover, as our understanding of the universe has grown more sophisticated, the limitations of the materialist worldview have become increasingly apparent. The emergence of phenomena like dark matter and dark energy, which defy explanation in terms of the known constituents of the physical world, have led some scientists to question the adequacy of the materialist paradigm and to explore alternative perspectives that might better account for the profound complexities and unexplained aspects of the cosmos. It is against this backdrop that the theory of biocentrism has emerged as a radical and often controversial challenge to the materialist consensus. By placing consciousness, rather than matter and energy, at the center of the cosmic tapestry, biocentrism offers a fundamentally different way of understanding the nature of reality and our place within it, one that has the potential to rewrite the very foundations of scientific and philosophical thought. At the heart of the biocentric worldview lies the radical proposition that consciousness is not merely a byproduct of physical processes, but rather a fundamental component of the universe itself, a primordial force that shapes and guides the very structure and evolution of existence. This bold and often unsettling assertion, which has been championed by the pioneering scientist and theorist Robert Lanza, stands in stark contrast to the prevailing materialist perspective, which holds that the physical world is the fundamental reality and that consciousness is merely an emergent property of complex biological systems. Instead, biocentrism suggests that the world we perceive is inextricably linked to the presence and activity of consciousness, and that the apparent laws and regularities of the physical universe may, in fact, be the product of the observing mind rather than an inherent property of existence itself. At its core, the biocentric view of the universe challenges the traditional distinction between the observer and the observed, the self and the world, proposing that these boundaries are ultimately artificial constructs that obscure the deeper truth of the fundamental interconnectedness of all things. Just as the principles of quantum mechanics have revealed the profound influence of the observer on the behavior of subatomic particles, biocentrism suggests that consciousness plays a crucial role in shaping the very fabric of reality, a revelation that has the potential to transform our understanding of the nature of existence and our place within it. Moreover, the biocentric perspective offers a radical reinterpretation of the origins and evolution of life, challenging the prevailing view that the emergence of consciousness is a mere byproduct of the increasingly complex physical and chemical processes that have shaped the development of the natural world. Instead, biocentrism proposes that consciousness may, in fact, be a fundamental component of the universe, guiding and shaping the very emergence of the material structures that we observe. This revolutionary idea, which has its roots in the philosophical and scientific explorations of thinkers as diverse as Arthur Schopenhauer, Henry Bergson, and John Wheeler, has the potential to upend our most deeply held assumptions about the nature of reality and the origins of the cosmos. For if consciousness is not merely an emergent property of the physical world, but rather a primordial force that lies at the very heart of existence, then the traditional distinctions between the subjective and the objective, the mental and the physical, may need to be radically re-examined and reinterpreted. One of the most compelling and intriguing aspects of the biocentric worldview is the way in which it resonates with and builds upon the insights of quantum mechanics, the revolutionary branch of physics that has transformed our understanding of the subatomic realm and challenged the very foundations of the materialist paradigm. At the heart of this connection lies the remarkable and often bewildering phenomenon known as the observer effect, the idea that the mere act of observing or measuring a quantum system can influence and alter the behavior of that system. This profound revelation, which emerged from the pioneering work of physicists like Niels Bohr and Werner Heisenberg in the early 20th century, challenged the long-held assumption that the physical world exists as a fixed objective reality, independent of the presence of an observer. Instead, the observer effect suggests that the quantum realm is fundamentally probabilistic and uncertain, with the act of observation playing a crucial role in determining the outcome of any particular measurement or experiment. And it is this profound connection between consciousness and the behavior of quantum systems that lies at the heart of the biocentric perspective. For if the mere act of observation can influence the behavior of subatomic particles, then it stands to reason that consciousness itself, the very essence of the observing mind, may play a more fundamental role in shaping the structure and evolution of the physical world. And it is this insight that forms the cornerstone of the biocentric worldview, which proposes that consciousness is not merely a byproduct of the physical universe, but rather a primordial force that lies at the very heart of existence itself. Moreover, the biocentric perspective offers a tantalizing new framework for reconciling the seemingly contradictory principles of quantum mechanics and general relativity, the two foundational pillars of modern physics that have long resisted a unified, self-consistent explanation. By placing consciousness at the center of the cosmic tapestry, biocentrism suggests that the apparent incompatibility between these two realms may be an artifact of our limited three-dimensional perspective, and that a deeper, more holistic understanding of the nature of reality may lie in the recognition of consciousness as a fundamental component of the universe. Indeed, as researchers have continued to explore the connections between the insights of quantum mechanics and the biocentric worldview, a wealth of tantalizing possibilities have emerged, from the potential for consciousness to shape the very structure of space-time to the possibility that the universe itself may be a manifestation of an underlying information-rich source plane that transcends the limitations of our three-dimensional perception. And as the exploration of these connections continues to unfold, the potential for unlocking the deepest secrets of the cosmos and rewriting our very conception of the nature of existence only seems to grow more tantalizing. For in the embrace of the biocentric perspective, we may well uncover the key to reconciling the apparent contradictions that have long plagued the scientific enterprise and to unveiling the true nature of the remarkable universe we inhabit. As the biocentric worldview has continued to evolve and gain traction within the scientific community, it has also led to a profound re-examination of some of the most fundamental questions about the nature of human consciousness, free will, and the self. If consciousness is indeed a primordial force that lies at the heart of existence, rather than a mere byproduct of physical processes, then the traditional notions of the self as a separate, autonomous entity may need to be radically reinterpreted. For if the boundaries between the observer and the observed are ultimately illusory, then the very concept of the individual, independent self that has long underpinned Western philosophy and psychology may be revealed as a convenient fiction, a construction of the mind that obscures the deeper truth of the fundamental interconnectedness of all things. Moreover, the biocentric perspective raises profound questions about the nature of free will and the degree to which our thoughts, actions, and decisions are truly our own. If the world we perceive is shaped and molded by the presence of consciousness, then the traditional notions of causality and determinism that have governed our understanding of the physical universe may need to be re-examined. And if the self is not a fixed, independent entity, but rather a fluid, ever-changing manifestation of the underlying unity of consciousness, then the very idea of individual agency and autonomy may need to be rethought. These are the kinds of profound and unsettling questions that have emerged from the exploration of biocentrism, and they have led to the development of a wealth of new frameworks and models for understanding the nature of consciousness, the self, and the human experience. From the philosophical musings of thinkers like David Chalmers and Bernardo Kastrup, to the cutting-edge neuroscientific research of individuals like Giulio Tononi and Michael Graziano, the quest to reconcile the insights of biocentrism with our traditional conceptions of the mind and the self has become a crucial frontier in the ongoing quest to unlock the deepest secrets of existence. And as this exploration has continued, a rich tapestry of interconnected ideas and perspectives has begun to emerge, one that draws upon the insights of quantum physics, the philosophy of consciousness, and the enduring mysteries of the cosmos. For in the embrace of the biocentric worldview, we are confronted with the possibility that the very foundations of our understanding of the self, the world, and the nature of reality may need to be radically rewritten. One of the most profound and transformative aspects of the biocentric worldview is its inherently holistic and interconnected perspective on the nature of existence. By placing consciousness at the center of the cosmic tapestry, biocentrism challenges the traditional Cartesian dualism that has long separated the mind from the physical world, and instead proposes a vision of reality in which the observer and the observed, the self and the other, are inextricably linked and interdependent. This shift in perspective, which echoes the insights of Eastern philosophies and the emerging field of systems theory, has the potential to profoundly reshape our understanding of the relationship between the individual and the larger whole, whether that whole is conceived of as the human organism, the ecosystem, the planet, or the universe itself. For if consciousness is indeed a fundamental component of the cosmos, rather than a mere byproduct of physical processes, then the traditional notions of the self as a separate, autonomous entity become increasingly untenable. Instead, the biocentric view suggests that the individual is but a manifestation of the larger field of consciousness that permeates and shapes the very fabric of existence, a revelation that has profound implications for our understanding of the nature of identity, the origins of life, and the meaning of our place within the grand cosmic drama. Moreover, the holistic vision of biocentrism extends beyond the boundaries of the self, offering a radical new perspective on the interconnectedness of all living things and the profound role that consciousness may play in the evolution and development of the natural world. Just as the observer effect in quantum mechanics suggests that the mere act of observation can influence and alter the behavior of subatomic particles, the biocentric view proposes that consciousness may be a driving force in the emergence and transformation of the myriad forms of life that populate the Earth and the cosmos beyond. This idea, which has been explored and developed by thinkers like Ervin Laszlo, James Lovelock, and Rupert Sheldrake, offers a profound challenge to the traditional Darwinian model of evolution, which has long emphasized the role of random mutation and natural selection as the primary drivers of biological change. Instead, the biocentric perspective suggests that the fundamental creativity and intelligence of consciousness may be intricately woven into the very fabric of the natural world, shaping and guiding the unfolding of life in ways that transcend the purely physical and mechanistic. And as the exploration of these ideas has continued, the potential for unlocking the deepest mysteries of existence only seems to grow more tantalizing. For in the embrace of the biocentric worldview, we may well uncover the key to reconciling the apparent contradictions that have long plagued our scientific and philosophical understanding of the cosmos, and to unveiling the profound and awe-inspiring truth of the fundamental interconnectedness of all things. As the exploration of biocentrism has continued to unfold, a wealth of tantalizing connections and parallels have emerged between this revolutionary perspective on the nature of reality and the insights of quantum mechanics, the holographic universe theory, and the enduring mysteries of consciousness itself. At the heart of this convergence lies the profound and often unsettling revelation that the behavior of quantum systems, with their apparent link to the act of observation and measurement, may offer crucial clues about the role of consciousness in shaping the very fabric of existence. For if the mere act of observing a quantum particle can influence and alter its behavior, then it stands to reason that consciousness, the very essence of the observing mind, may play a far more fundamental role in the unfolding of reality than the traditional materialist worldview has allowed. This connection between the quantum realm and the primacy of consciousness lies at the very core of the biocentric perspective, which proposes that the world we perceive is not an independent, objective truth, but rather a fluid, ever-shifting manifestation of the underlying field of consciousness that permeates and shapes the cosmos. Moreover, the bias-centric view finds further resonance in the radical insights of the holographic universe theory, the bold and often counterintuitive proposition that our perceived three-dimensional reality may, in fact, be a holographic projection of a deeper two-dimensional source. For if consciousness is indeed a fundamental component of the universe, rather than a mere byproduct of physical processes, then the very structure and organization of the physical world may need to be reinterpreted in light of this profound insight. Indeed, the connections between biocentrism, quantum mechanics, and the holographic universe theory are truly profound and far-reaching. By placing consciousness at the center of the cosmic tapestry, the biocentric worldview offers a potential pathway to reconciling the seemingly contradictory principles of these disparate realms of scientific inquiry, providing a unified framework for understanding the true nature of existence and the role of the observer in shaping the very fabric of reality. Moreover, the exploration of these interconnected ideas has the potential to yield transformative insights into the nature of consciousness itself, insights that may well rewrite our very conception of the self, the mind, and the purpose of human existence. In the grand tapestry of the universe, there exists a profound and often bewildering phenomenon that has captivated the scientific imagination for decades, the remarkable and seemingly inexplicable process known as quantum entanglement. This strange, often counterintuitive principle, which lies at the very heart of the quantum realm, challenges our most fundamental notions about the nature of reality and the relationship between the observer and the observed, offering a tantalizing glimpse into the profound interconnectedness that may lie at the core of existence itself. At its essence, quantum entanglement refers to the remarkable ability of two or more quantum particles to become inextricably linked, such that the state of one particle cannot be fully described without reference to the state of the other. This bizarre and often perplexing phenomenon, which was famously dismissed by Albert Einstein as spooky action at a distance, lies at the very heart of the quantum revolution that has transformed our understanding of the physical world, offering a window into a realm where the familiar rules of classical physics no longer apply. For in the quantum realm, the boundaries between the self and the other, the observer and the observed, become increasingly blurred and indistinct. When two or more particles become entangled, their individual identities seem to merge, giving rise to a unified system that defies our traditional notions of causality, locality, and the separation of the physical world into distinct, independent entities. And as researchers have continued to explore the remarkable properties and implications of quantum entanglement, they have uncovered a wealth of tantalizing insights and possibilities, from the potential for harnessing the power of entangled systems in cutting-edge technologies like quantum computing and quantum cryptography, to the profound philosophical and metaphysical questions that arise from the recognition of the fundamental interconnectedness of all things. Indeed, the study of quantum entanglement has become a crucial frontier in the ongoing quest to unlock the deepest secrets of the universe and to reconcile the seemingly contradictory principles of quantum mechanics and general relativity. For in the embrace of this extraordinary phenomenon, we may well uncover the key to understanding the true nature of reality and our place within the grand cosmic tapestry. At the heart of quantum entanglement lies the remarkable and often counterintuitive behavior of subatomic particles, the electrons, photons, and other fundamental entities that make up the building blocks of the physical world. According to the principles of quantum theory, these tiny, elusive particles can exist in a state of superposition, occupying multiple possible states simultaneously until they are observed or measured. And when two or more of these quantum particles become entangled, their individual states become inextricably linked, such that the measurement or observation of one particle can instantly influence the state of the other, even if they are separated by vast distances. This remarkable phenomenon, which seems to defy the very notion of causality and the speed of light, has been the subject of intense scientific scrutiny and debate for decades, as researchers have sought to unravel the mysteries of the quantum realm and to understand the true nature of the physical world. At the heart of this entanglement is the concept of the wave function, the mathematical description of the state of a quantum system that encodes all the possible outcomes of any measurement or observation that might be performed on that system. When two or more particles become entangled, their individual wave functions become intertwined, effectively merging their identities into a single unified system. And it is this unity, this profound interconnectedness at the quantum level, that gives rise to the remarkable and often counterintuitive phenomena associated with entanglement. For when one entangled particle is observed or measured, the state of the other particle instantly changes, as if the two are communicating instantaneously, a finding that seems to challenge the very foundations of our classical understanding of the physical world. Indeed, the implications of this quantum entanglement are truly profound, for they suggest that the fundamental building blocks of the universe may not be the distinct, independent entities we perceive, but rather a deeply interconnected web of relationships and interactions that defy our most deeply held assumptions about the nature of reality. And as researchers have continued to explore the remarkable properties and behaviors of entangled systems, they have uncovered a wealth of tantalizing insights and possibilities, from the potential for harnessing the power of entanglement in cutting-edge technologies to the profound philosophical and metaphysical questions that arise from the recognition of the fundamental oneness of all things. While the philosophical and metaphysical implications of quantum entanglement have captivated the minds of scientists and thinkers for decades, the practical applications of this remarkable phenomenon have also begun to emerge as a crucial frontier in the world of modern technology and scientific research. One of the most exciting and promising areas of exploration in this regard is the field of quantum computing, a revolutionary new approach to information processing that leverages the unique properties of entangled quantum systems to achieve feats of computation and data analysis that are simply impossible using traditional, classical approaches. At the heart of quantum computing is the remarkable ability of entangled particles to exist in a state of superposition, occupying multiple possible states simultaneously. By harnessing this quantum weirdness, researchers have been able to develop new algorithms and computational models that can tackle problems that would take even the most powerful classical computers billions of years to solve. From the factorization of large numbers to the simulation of complex chemical and physical systems, the potential applications of quantum computing are truly staggering. And as the technology continues to evolve and advance, the prospect of unlocking the full power of entanglement to revolutionize fields ranging from cryptography to material science has become an increasingly tantalizing and ambitious goal. But the practical applications of quantum entanglement extend far beyond the realm of computing. In the field of quantum cryptography, for example, researchers have leveraged the unique properties of entangled photons to develop new methods of secure communication that are virtually unbreakable, even in the face of the most sophisticated hacking attempts. By encoding information in the quantum states of entangled photons, these cutting-edge cryptographic systems can detect the presence of any eavesdropping or interference, ensuring the absolute privacy and security of the transmitted data. And as the world becomes increasingly reliant on digital communication and the exchange of sensitive information, the development of quantum-based security protocols has become a crucial priority for governments, corporations, and individuals alike. Moreover, the potential applications of quantum entanglement extend far beyond the realms of computing and cryptography. In fields ranging from quantum sensing and metrology to the exploration of the fundamental nature of the universe, researchers have begun to harness the remarkable properties of entangled systems to push the boundaries of scientific discovery and technological innovation. From the development of ultra-precise atomic clocks and gravitational wave detectors to the investigation of the deepest mysteries of the cosmos, The promise of quantum entanglement lies in its ability to provide unprecedented levels of sensitivity, precision, and insight, a revelation that has the potential to transform our understanding of the physical world and our place within it. But the significance of quantum entanglement extends far beyond its practical applications, for this remarkable phenomenon also carries with it a wealth of profound philosophical and metaphysical implications that have the potential to transform our very conception of the nature of reality and our place within it. At the heart of this philosophical exploration lies the profound and often unsettling revelation that the boundaries between the self and the other, the observer and the observed, may not be as distinct and impermeable as we have long assumed. For if the fundamental building blocks of the universe can become so profoundly and inextricably linked that the state of one particle can instantly influence the state of another, regardless of the distance between them, then the traditional notions of causality, locality, and the separation of the physical world into distinct, independent entities begin to crumble. Indeed, the very idea of quantum entanglement seems to challenge the most deeply held assumptions of the materialist worldview, which has long held that the physical universe exists as an independent, objective reality governed by a fixed and deterministic set of rules. For if the behavior of these fundamental particles is so profoundly influenced by the mere act of observation and measurement, then how can we ever hope to achieve a truly objective, observer-independent understanding of the nature of existence? Moreover, the philosophical and metaphysical implications of quantum entanglement extend far beyond the realm of physics, touching upon the most profound and enduring questions about the nature of consciousness, the self, and the very essence of being. For if the universe is imbued with a fundamental interconnectedness at the quantum level, then how might this challenge our traditional notions of individuality, free will, and the boundaries of the self? These are the kinds of questions that have captivated the minds of philosophers, mystics, and curious thinkers for generations, and the insights of quantum entanglement have only served to amplify their urgency and relevance. From the Buddhist concepts of non-duality and the interconnectedness of all things to the Western philosophical explorations of the mind-body problem and the nature of consciousness, the principles of quantum entanglement have the potential to radically transform our understanding of the self, the world, and the very fabric of existence. Indeed, as researchers have continued to delve into the mysteries of quantum entanglement, they have uncovered a wealth of tantalizing connections and parallels with a diverse array of spiritual and philosophical traditions, from the holistic worldviews of Eastern philosophy to the mystical insights of various religious and esoteric lineages. And in the embrace of these interconnected perspectives, the potential for unlocking the deepest secrets of the universe and our place within it only seems to grow more tantalizing. As the exploration of quantum entanglement has continued to unfold, a remarkable and often unexpected connection has emerged between this profound phenomenon and the radical insights of the holographic universe theory, the bold and counterintuitive proposition that our perceived three-dimensional reality may, in fact, be a holographic projection of a deeper two-dimensional foundation. At the heart of this connection lies the profound observation that the properties of entangled quantum systems seem to mirror the underlying principles of the holographic principle, the idea that the total information content of a given region of space is proportional to the two-dimensional surface area of its boundary, rather than its three-dimensional volume. Indeed, the remarkable ability of entangled particles to instantaneously influence one another, even when separated by vast distances, has led some researchers to propose that the very fabric of the physical world may be a manifestation of an underlying, information-rich source plane that transcends the limitations of our three-dimensional perception. Just as a three-dimensional image can be encoded and reconstructed from the information contained on a two-dimensional holographic film, the proponents of the holographic universe theory argue that the entire cosmos we inhabit may be a holographic projection of a deeper, more fundamental reality. And if this radical proposition were to be true, then the profound interconnectedness revealed by the principles of quantum entanglement may offer crucial clues about the true nature of this underlying reality. For if the physical world is, in fact, a holographic manifestation of a deeper two-dimensional foundation, then the remarkable ability of entangled particles to transcend the boundaries of space and time may be a reflection of the fundamental oneness and unity that lies at the heart of existence. Moreover, the connections between quantum entanglement and the holographic universe theory extend far beyond the realm of pure speculation, as researchers have begun to uncover tantalizing evidence of the deep and abiding links between these two revolutionary concepts. From the resolution of long-standing paradoxes in the study of black holes to the potential for a deeper understanding of the origins and evolution of the cosmos, the exploration of these interconnected ideas has become a crucial frontier in the ongoing quest to unlock the deepest secrets of the universe. Indeed, as the exploration of quantum entanglement and the holographic universe theory has continued to unfold, the potential for transformative insights and a radical rewriting of our understanding of the physical world only seems to grow more tantalizing. For in the embrace of these extraordinary principles, we may well uncover the key to reconciling the apparent contradictions that have long plagued our scientific and philosophical understanding of the cosmos, and to unveiling the profound and awe-inspiring truth of the fundamental interconnectedness of all things. As we have delved into the remarkable and often bewildering phenomenon of quantum entanglement, it has become increasingly clear that this profound and enigmatic principle lies at the very heart of our understanding of the physical world and our place within it. For in the embrace of this extraordinary revelation, we are confronted not only with the limitations of our scientific knowledge, but also with the most fundamental questions about the nature of existence itself. Indeed, the study of quantum entanglement has the power to transform our very conception of reality, challenging the traditional boundaries between the observer and the observed, the self and the other, and the fundamental constituents of the physical world. And as researchers have continued to explore the profound implications of this remarkable phenomenon, they have uncovered a wealth of tantalizing possibilities and unsettling questions that have the potential to rewrite the very foundations of our understanding of the cosmos. From the practical applications of entanglement in cutting-edge technologies like quantum computing and cryptography, to the profound philosophical and metaphysical insights that emerge from the recognition of the fundamental interconnectedness of all things, the exploration of this quantum enigma has become a crucial frontier in the ongoing quest to unlock the deepest secrets of the universe. And as we continue to grapple with the mysteries of entanglement, the potential for unlocking transformative insights only seems to grow more tantalizing. For in the embrace of this extraordinary phenomenon, we may well uncover the key to reconciling the apparent contradictions that have long plagued our scientific and philosophical understanding of the physical world, and to unveiling the profound and awe-inspiring truth of the fundamental oneness that lies at the very heart of existence. Whether the ultimate destination of this journey is a radical new theory that upends our most deeply held assumptions about the nature of reality, or merely a testament to the enduring mystery and complexity of the universe we inhabit, the exploration of quantum entanglement promises to be a transformative and captivating endeavor. For in the face of this quantum enigma, we are compelled to confront the very limits of our knowledge and to embrace the profound and unsettling possibilities that lie beyond the boundaries of our understanding. And as we continue to push the frontiers of scientific inquiry and to grapple with the most fundamental questions about the nature of existence, the insights gleaned from the study of quantum entanglement may well hold the key to unlocking the deepest secrets of the cosmos. For in the embrace of this extraordinary phenomenon, we may find not only the answers to our most pressing questions, but also the inspiration to expand the horizons of our knowledge and to confront the most profound mysteries of the universe with a renewed sense of wonder and curiosity. In the grand tapestry of modern scientific exploration, few concepts have captivated the imagination and challenged the boundaries of our understanding more profoundly than the notion of the multiverse, the radical proposition that our perceived reality may be but one of countless, parallel universes coexisting within a grander, multidimensional realm of existence. This extraordinary idea, which has its roots in the mind-bending principles of quantum mechanics and the search for a unified theory of the physical world, represents a profound departure from the traditional single-universe model that has long dominated our scientific and philosophical conceptions of reality. For if the multiverse hypothesis were to be true, it would not only transform our understanding of the cosmos and our place within it, but also force us to confront the most fundamental questions about the nature of existence itself. At the heart of the multiverse theory lies the remarkable and often counterintuitive behavior of subatomic particles, the tiny, elusive entities that make up the fundamental building blocks of the physical world. According to the principles of quantum mechanics, these quantum particles can exist in a state of superposition, occupying multiple possible states simultaneously until they are observed or measured. And it is this quantum weirdness, this fundamental uncertainty, that lies at the core of the multiverse hypothesis. For if the behavior of quantum particles is fundamentally probabilistic and uncertain, then the very notion of a single definitive reality may need to be radically re-examined. Perhaps the proponents of the multiverse theory argue the act of observation or measurement does not simply reveal a pre-existing state of the universe, but rather selects one possible outcome from a multitude of parallel realities, each one a distinct and equally valid manifestation of the underlying quantum realm. This profound and often unsettling idea, which has been explored and developed by a host of renowned physicists, from Hugh Everett and John Wheeler to Stephen Hawking and Max Tegmark, challenges the very foundations of our classical understanding of the physical world. For if the multiverse hypothesis were to be true, then the boundaries between the observer and the observed, the self and the other, would become increasingly blurred and indistinct, a revelation that has the potential to transform our most deeply held assumptions about the nature of consciousness, free will, and the very essence of existence. Indeed, as researchers have continued to delve into the mysterious and often counterintuitive implications of the multiverse theory, a wealth of profound and often unsettling questions have emerged, questions that touch upon the very heart of our understanding of reality and our place within it. From the possibility of infinite, parallel versions of ourselves to the nature of consciousness and the role of the observer in shaping the unfolding of existence, the exploration of the quantum multiverse has become a crucial frontier in the ongoing quest to unlock the deepest secrets of the universe. The origins of the multiverse hypothesis can be traced back to the early days of quantum mechanics, when pioneering physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger were grappling with the profound and often bewildering implications of the quantum realm. At the heart of this revolution in our understanding of the physical world was the remarkable and counterintuitive behavior of subatomic particles, the electrons, photons, and other fundamental entities that make up the building blocks of the universe. According to the principles of quantum theory, these tiny, elusive particles can exist in a state of superposition, occupying multiple possible states simultaneously until they are observed or measured. This finding, which challenged the long-held assumptions of classical physics and the notion of a fixed deterministic reality, led to the development of the Copenhagen interpretation of quantum mechanics, a perspective that emphasized the fundamental role of the observer in shaping the behavior of quantum systems. And it was from this radical departure from the Newtonian worldview that the seeds of the multiverse hypothesis began to take root. For if the mere act of observation or measurement can collapse the wave function of a quantum particle, selecting one possible state from a multitude of potential outcomes, then it stands to reason that the unobserved possibilities may continue to exist as parallel, equally valid realities. This idea, first proposed by the American physicist Hugh Everett in the 1950s, came to be known as the many worlds interpretation of quantum mechanics, and it laid the foundation for the more expansive and far-reaching multiverse theory that would emerge in the decades to come. Moreover, the philosophical and metaphysical implications of this quantum weirdness have continued to captivate the minds of scientists and thinkers alike. If the boundaries between the observer and the observed, the self and the world, can be so profoundly blurred and blended at the quantum level, then what might this reveal about the true nature of existence and our place within it? And if the universe we inhabit is but one of countless, equally real parallel realms, then how might this challenge our most deeply held assumptions about the origins, structure, and purpose of the cosmos? These are the kinds of profound and unsettling questions that have driven the exploration of the multiverse hypothesis, as researchers have sought to reconcile the insights of quantum mechanics with the enduring mysteries of the physical world. And as this quest has continued to unfold, a wealth of new and often unexpected possibilities have emerged, each one offering a tantalizing glimpse into the complex and multifaceted nature of reality. At the heart of the multiverse hypothesis lies the remarkable and often bewildering concept of parallel universes, the idea that our perceived reality is but one of countless, equally valid manifestations of the underlying quantum realm, each one a unique and distinct universe coexisting within a grander, multidimensional expanse of existence. This extraordinary proposition, which has been explored and developed by a host of renowned physicists and cosmologists, challenges the traditional single-universe model that has long dominated our scientific and philosophical conceptions of reality. For if the multiverse hypothesis were to be true, it would not only transform our understanding of the cosmos and our place within it, but also force us to confront the most fundamental questions about the nature of consciousness, free will, and the very essence of being. At the heart of this multiverse theory lies the remarkable behavior of quantum particles, which can exist in a state of superposition, occupying multiple possible states simultaneously until they are observed or measured. According to the many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in the 1950s, each of these potential outcomes represents a distinct and equally real parallel universe, branching off from the others as the wave function of the quantum system collapses into a specific state. This idea, which has been further developed and expanded upon by a host of other physicists and cosmologists, suggests that the universe we inhabit is but one of an infinite number of parallel realities, each one a unique manifestation of the underlying quantum possibilities. And as the fundamental particles and fields that make up the fabric of reality interact and evolve, the multiverse continues to spawn new and ever more complex branches, creating a vast, interwoven tapestry of existence that transcends the boundaries of our three-dimensional perception. But the implications of the multiverse hypothesis extend far beyond the realm of pure theory and speculation. For if this radical proposition were to be true, it would not only challenge our most deeply held assumptions about the nature of the physical world, but also profoundly transform our understanding of consciousness, free will, and the very essence of the self. After all, if the universe we inhabit is but one of countless, equally valid parallel realities, then what might this mean for our sense of personal identity and agency? Are we, in fact, the unique and autonomous individuals we believe ourselves to be, or merely one of an infinite number of versions of ourselves, each with its own distinct experiences and choices? And how might the recognition of the multiverse fundamentally reshape our notions of morality, responsibility, and the purpose of existence? These are the kinds of profound and unsettling questions that have captivated the minds of scientists, philosophers, and curious thinkers alike, as they have sought to grapple with the mind-bending implications of the multiverse hypothesis. And as research in this field has continued to evolve, a wealth of new and often unexpected possibilities have emerged, each one offering a tantalizing glimpse into the complex and multifaceted nature of reality. As the exploration of the multiverse hypothesis has continued to unfold, a remarkable and often unexpected connection has emerged between this radical proposition and the long-standing quest to develop a unified, comprehensive theory of the physical world, a theory of everything that can reconcile the insights of quantum mechanics and general relativity and unlock the deepest secrets of the cosmos. At the heart of this connection lies the profound observation that the multiverse, with its emphasis on the existence of parallel universes and the fundamental role of quantum mechanics, may hold the key to resolving the seemingly irreconcilable differences between these two foundational pillars of modern physics. For if the universe we inhabit is but one of an infinite number of parallel realities, each one a unique manifestation of the underlying quantum realm, then the apparent contradictions between the probabilistic, counterintuitive principles of quantum theory and the deterministic geometric descriptions of general relativity may begin to dissolve. Indeed, the multiverse hypothesis has been embraced by a growing number of physicists and cosmologists as a potential pathway to the long-sought-after theory of everything, a unifying framework that can accommodate the insights of both the subatomic and the cosmic scales, and provide a comprehensive, self-consistent explanation for the fundamental structure and behavior of the physical world. At the heart of this approach lies the radical proposition that the various parallel universes that make up the multiverse may, in fact, be governed by slightly different sets of physical laws and fundamental constants, a revelation that has the potential to unlock new avenues of exploration and discovery. By studying the properties and behaviors of these distinct, yet equally valid parallel realities, researchers may be able to gain invaluable insights into the underlying nature of the laws and principles that define the physical universe, and to uncover the deeper, more fundamental principles that have eluded our grasp for so long. Moreover, the multiverse hypothesis offers the tantalizing prospect of resolving long-standing paradoxes and conundrums that have vexed physicists for decades. From the information paradox surrounding black holes to the enduring mysteries of dark matter and dark energy, the multiverse may hold the key to unraveling the deepest secrets of the cosmos and reconciling the apparent contradictions that have long plagued our scientific understanding. Indeed, as the exploration of the multiverse has continued to evolve, a wealth of new and often unexpected connections have emerged between this radical proposition and the cutting-edge frontiers of modern physics. From the insights gleaned about the origins and evolution of the universe to the potential implications for the nature of space, time, and the very fabric of existence, the multiverse hypothesis has become a crucial component in the ongoing quest to develop a comprehensive, unified theory of the physical world. And as this quest continues to unfold, the potential for unlocking transformative insights only seems to grow more tantalizing, for in the embrace of the multiverse, we may well uncover the key to reconciling the apparent contradictions that have long plagued our scientific and philosophical understanding of the cosmos, and to unveiling the profound and awe-inspiring truth of the fundamental interconnectedness of all things. As the exploration of the multiverse hypothesis has continued to captivate the minds of scientists and thinkers alike, a wealth of profound and often unsettling questions have emerged about the nature of consciousness and its role in shaping the fabric of reality. For if the universe we inhabit is but one of countless, equally valid parallel realities, each one a unique manifestation of the underlying quantum realm, then the very notion of the self, the individual, and the boundaries of the conscious mind may need to be radically re-examined and reinterpreted. After all, if the multiverse hypothesis were to be true, then each of us would not be a singular, unique entity, but rather one of an infinite number of versions of ourselves, each with its own distinct experiences, choices, and perspectives. And the recognition of this profound interconnectedness, this fundamental blurring of the boundaries between the self and the other, has the potential to transform our most deeply held assumptions about the nature of consciousness, free will, and the meaning of existence itself. Indeed, the implications of the multiverse for our understanding of the mind and the self are truly profound and far-reaching. For if the universe is truly a multidimensional tapestry of parallel realities, then the traditional Cartesian dualism that has long separated the mind from the physical world may need to be radically reinterpreted. And the very notion of individual agency and autonomy, the bedrock of our conception of personal identity and moral responsibility, may be revealed as a convenient fiction of skewing the deeper truth of the fundamental interconnectedness of all things. Moreover, the multiverse hypothesis offers the tantalizing prospect of unlocking new and unexpected insights into the nature of consciousness and its role in shaping the fabric of reality. For if the mere act of observation and measurement can collapse the wave function of a quantum system, selecting one possible outcome from a multitude of parallel realities, then what might this reveal about the deep and abiding connection between the observing mind and the unfolding of existence? These are the kinds of profound and unsettling questions that have captivated the minds of philosophers, neuroscientists, and curious thinkers alike, as they have sought to grapple with the radical implications of the multiverse for our understanding of the self, the mind, and the very essence of being. And as research in this field has continued to evolve, a wealth of new and often unexpected possibilities have emerged, each one offering a tantalizing glimpse into the complex and multifaceted nature of consciousness and its role in the grand cosmic tapestry. As the exploration of the multiverse hypothesis has continued to unfold, a wealth of profound and often unsettling questions have emerged about the true nature of existence and our place within the grand cosmic drama. For if the universe we inhabit is but one of countless, equally valid parallel realities, each one a unique manifestation of the underlying quantum realm, then the very foundations of our understanding of the physical world, the self, and the purpose of life itself may need to be radically re-examined and reinterpreted. At the heart of these questions lies the profound and often bewildering revelation that the traditional notions of causality, determinism, and the separation between the observer and the observed may be little more than convenient fictions, artifacts of our limited, three-dimensional perspective on the true nature of reality. For if the multiverse hypothesis were to be true, then the very boundaries between the self and the world, the individual and the collective, may be far more blurred and indistinct than we have ever imagined. Indeed, the implications of the multiverse for our understanding of the meaning and purpose of existence are truly vast and far-reaching. If the universe is truly a multidimensional tapestry of parallel realities, each one a unique and equally valid manifestation of the underlying quantum realm, then the traditional notions of fate, free will, and the nature of personal identity may need to be radically reinterpreted. Are we, in fact, the autonomous, self-determining individuals we believe ourselves to be, or merely one of an infinite number of versions of ourselves, each with its own distinct experiences and choices? And if the multiverse is truly the bedrock of existence, then what might this mean for our understanding of the origins of life, the evolution of consciousness, and the very purpose and meaning of our individual and collective existence? These are the kinds of profound and unsettling questions that have captivated the minds of philosophers, theologians, and curious thinkers alike, as they have sought to grapple with the radical implications of the multiverse hypothesis. And as research in this field has continued to evolve, a wealth of new and often unexpected possibilities have emerged, each one offering a tantalizing glimpse into the complex and multifaceted nature of existence itself. From the exploration of the deep interconnectedness that may lie at the heart of the multiverse to the potential for unlocking new and unexpected insights into the nature of consciousness and the self, the quest to understand the true nature of existence has become a crucial frontier in the ongoing scientific and philosophical exploration of the cosmos. And as we continue to push the boundaries of our knowledge and to confront the unexpected, the potential for transformative insights only seems to grow more tantalizing. As we have delved into the profound and often bewildering implications of the multiverse hypothesis, it has become increasingly clear that this radical proposition represents a profound challenge to our most deeply held assumptions about the nature of reality, the self, and the very fabric of existence. For in the embrace of the multiverse, we are confronted not only with the limitations of our scientific knowledge, but also with the most fundamental questions about the true essence of being and our place within the grand cosmic tapestry. Indeed, the exploration of the multiverse has the power to transform our very conception of the physical world, challenging the traditional notions of causality, determinism, and the separation between the observer and the observed. And as researchers have continued to uncover the tantalizing connections between this radical proposition and the insights of quantum mechanics, general relativity, and the enduring mysteries of consciousness, the potential for unlocking transformative insights only seems to grow more tantalizing. Quantum physics emerged as scientists realized classical mechanics could not explain observations on microscopic scales. Max Planck's discovery of light quanta and Albert Einstein's photoelectric effect theory showed light and matter behave as both particles and waves. Niels Bohr incorporated this into his model of the atom, which successfully explained atomic spectra. Further, Werner Heisenberg's uncertainty principle placed fundamental limits on simultaneously knowing some properties like position and momentum. Important quantum principles include wave-particle duality, exhibited by photons and electrons, which have particle-like and wave-like aspects. Quantum tunneling allows particles to pass through barriers they could classically surmount. Entanglement non-locally links properties of particles even over large separations. Quantum computing uses qubit superpositions and algorithms to solve problems exponentially faster than classical computers for certain applications like factoring. Quantum dots confine electrons to discrete energy levels like atoms, enabling tailored optical and electronic behaviors. Quantum cryptography distills secure keys by detecting eavesdropping through violations of Bell's theorem predicted by entangled photons. Attempts to merge quantum mechanics and general relativity into a theory of quantum gravity aim to resolve challenges at small space-time scales near the Planck length. Advancing our comprehension of these quantum phenomena continues revolutionizing science and technology. While many fundamental questions remain open, progresses are steadily expanding our visions of reality on microscopic scales by applying quantum theories. Future breakthroughs may address long-standing mysteries or enable radically new capabilities through continued experimental and theoretical developments across the realms, where classical descriptions break down and nature exhibits her most enigmatic quantum behaviors. Thank you for watching this video. This is Jack, and see you on the next video. Subscribe to